Здесь также все.
Да, здесь.
Давайте послушаем. Мне кажется, удобно. Все, норм. Как это закрывать? Как это выключить?
Такая сложность.
Так.
В принципе, со всех мест
Они все
работают.
То есть я могу... Все. Спасибо.
Вы определитесь, и мы скажем тогда вот еще оператор.
Начну здесь, наверное, потому что у меня доклад отдельно. Okay, good afternoon, ladies and gentlemen. I think we can start because slow delay, and I'm glad to welcome you here in this wonderful hall. It's named Presidential Hall, and I'm also very thankful to open section of laser matter interaction, part 2, today, second day. And let's speak about time of presentation. It's approximately 12 minutes and 3 minutes for questions. And for first presentation, I want to ask, introduce first presenter. I'd like to invite Dr. Sinyov, please.
To start off our session today, first talk is from Dr. Ilya Tunkin from Institute of Chemistry, St. Petersburg State University, who will give a presentation on the direct laser writing of copper micropatterns from deep eutectic solvents, chemical and physical aspects. Please, floor is yours.
Thank you very much once again. And I'd like to present my talk related to direct laser writing of metal micropatterns from deep eutectic solvents, chemical and physical aspects. And my name is Ilya Tunkin. I'm from St. Petersburg State University, laser microfabrication lab, Institute of Chemistry. Outline of my presentation, you can see on the slide. It's first I give some introduction about this technique and application, and second one I'd like to give some words about application of direct laser writing of the metal. Next I move to laser deposition technique, how we create some patterns on different substrates, and next I'll give information about direct laser writing of micropatterns from deep eutectic solvents, and a few words about chemical and physical parameters of this process. And last part of my presentation will be about application of metal patterns like a sensory platform for electrochemical detection. Okay, let's start. Today, very important things to create some technology for application of different patterns on the surface of glass and ceramics, polymer materials, and so on. And people from different fields, scientists from different fields, try to create new technology for instead of conventional, traditional photolithography technique, and try to make this technology more easily and precise and selective. Here you can see, I think it's a wonderful paper about related to this field, about different approach for fabrication metal patterns using laser, and not only laser, electrochemical one. And about application, there are different applications of these materials. It depends on which substrate we can use, or which metal or composite materials we can use for creation of these devices. If we fabricate metal patterns on the part, creation biosensors for detection different gases for environmental, and fabrication of electrochemical sensors for detection some analytes in human body. Let's speak a few words about different approaches for laser-induced metal deposition. Here you can see three interesting technique when they use laser. It's first one, it's femtosecond laser pulse induced reductive sintering. It's traditional, it's different from traditional sintering, when in this case we use some ink consist nanoparticles of metal oxide, for example nickel or cobalt and copper and so on. And we can, after that we can create patterns just right on the surface, and after we need to remove this layer, unreactive layer. Second one is most known, it's laser-induced forward transfer, when we need laser beam which focused on the donor substrate, and below this placed receiver like acceptor substrate, which on this substrate we can fabricate some small and beautiful patterns and dots and so on. And third one, it's very promising technology, laser-induced selective metallization, when they use multi-steps for creation metal patterns. For example, here it's copper patterns, when the laser source used for activation and activation of the surface. Next one, some chemical solution consists salt of silver used for create some layer, which after that for copper plating solution used for create some films or patterns on the surface. But nevertheless, this technology is very promising, but some disadvantages, has some disadvantages. For example, it's multi-steps, like here, and some very not so very expensive equipment in case of femtosecond laser, and also some difficult creation of difficult ink in case of laser-induced forward lift technology. For this reason, more than 20 years, researchers from different group from Europe start to use laser source for and some here you can see like cells with cathode which use for substrate and laser source for drive this process. Oh, sorry, it's me. Yeah, but it helps to localize reaction not on this area, but localize it on the small area in this area when a laser beam is affected. Next step was performed by group Professor Shafeev in Moscow, and next in our university next step was performed by group of Professor Manshina, and they create beautiful metal patterns from just salts of metal for create patterns, dots, and so on. And a few words about laser-induced deposition. It's technique which helps us to create metal patterns from different plating solution using laser without applied voltage and so on. It's just a combination of chemical, electrochemical and laser deposition. And for example, we use neodymium YAG laser, CV laser, which focus on the substrate, which immersed on the solution, and laser beam just create metal patterns from the solution, which can help create beautiful patterns. You can see picture, optical image is here. And also our team shown that we can change chemical parameters, chemical composition for creates different surface of the metal patterns, and also create bimetallic and not only copper and also silver, aurum and nickel and cobaltum and so on. But despite on this speed of this process, deposition from solution, I mean, it's very slow. It's not applicable for technology. For this reason, many researchers try to find best solution for solve this problem, and one of this solution is use deep eutectic solvents like media for laser-induced deposition. And we, in our work, we show that that possible increase deposition of the metal from this value to 500 micrometers per second and even more when I show today. What is the deep eutectic solvents? How is it deep? And what is the chemical substances? You can see here on the table, sorry, that's left column, it's just acceptor of proton, but in our case we use halide chloride, it's quaternary ammonium salts, and also hydrogen bond donors, for example, urea and alcohols and some acids. And here you can see the diagram of the when we mixed this substance, the temperature of this melting is decreased, and we can see eutectic points here. And why we use deep eutectic solvents and where also it can be used. Here you can see the small picture about different application. Its main applications in chemistry, it's analytical chemistry for extraction of different substance, different analytes from food, from many applications. But also interesting application for creation patterns and coatings using electrochemical technique. And in this case we try to use laser sources for creation patterns from deep eutectic solvents. Why we use it? Because it's eco-friendly, because it's water-soluble, using very low melting point. It's very important for laser radiation, and very useful for mix these substances. And our first result was when we applied this deposition from deep eclectic solvents, we can increase deposition speed from 100 and more times using this system. And we show that the three-component deep eclectic solvents, choline chloride, you can see here some organic acids, and salt of chloride, and for example acetate of copper, can use and connect formation of hydrogen bond and use like media for laser deposition. Why? Which factors we should solve and we should decide about this? It's physical factors, laser radiation of wavelengths and power, scanning speed, and so on. And chemical factors, composition of solution and concentration of these components, and so on. And also main parameters, it's surface properties of the surface. It's we need activation or some additional preparation for surface. And here you can see the picture of the how we can prepare deep eclectic solvents and prepare some patterns. It's very easy and very cheap. We just need to mix these three components and mix it and boil and just hot on the magnetic or heater stirrer, and after we should cover the glass or another type of substrate and radiate laser and just wash it using water. It's very easy. And in the result we can fabricate some patterns consist from the pure copper. You can see here our XRD result. And next we try to find best parameter for find chemical composition. We need to collect this puzzle, and we find that from different organic acid we use citric, succinic, and so on. Best parameter for citric and tartratic acid lead to formation of this slide. I think I can skip because it's mechanism for chemical decomposition of this solution, which leads to creation of patterns. And here our recent result, I think it's very beautiful, to use additional of some sugar alcohols and carbohydrate, and for this mixture, and we can use D-glucose, D-fructose, and so on, for create these beautiful patterns from the surface of the glass. You can see also SEM images and XRD investigations. And here we demonstrate our possibilities to fabricate on non-planar surface, and if we change the parameter and solution, we can fabricate homogeneous patterns or some like flowers and so on. I want to introduce next presentation about this application. The speech will be done by by Dr. Dmitry Sinyov, and he skip on this more detail about fabrication from infrared beam. And also with collaboration with Dr. Lagunov, he made presentation yesterday. We they try to fabricate and coating procedure of coating of this solution, and it's possible to create some beautiful structures with and width of this one line from 10 and even less micrometers. And here you can see some video. its fabrication process. It's very easy to fabricate. And also one big advantage is how we can remove non-radiative layer. It's just using water, and our patterns is ready. And here, our application, we applied this technique for electrochemical detection of some analytes in solution. And next, we move to analyze different substance in the human blood and saliva and so on. Here we can see result detection of dopamine and acetaminophenol. It's like paracetamol, acetaminophenol, and we can detect it in the mix of solution. And I want to conclude, and we have proposed a new one type of media for laser direct writing of metal, named it's the deep eutectic solvents. Applied different sources, laser sources for creation of patterns from infrared and nanosecond and picosecond laser. And also shown that we can apply these patterns like electrode for electrochemical detection. What's next? Next we want to create some patterns, some platform which we use, which we fabricate from different solution, from third step on just less, and use it for like tape and platforms for detection analytes. And I want to thank our team, and our PhD student, our student, and our colleague engineer, and also I want to thank our collaborator, Dr. Lagunov, Dr. Sinyov, they from ITMO University, and Dr. Andrei Shishov from St. Petersburg State University. And also I want to thank grants, Russian Science Foundation. And if we also open for collaboration, if we have some questions, you can write mail or some just mobile phone and call or write me, and I answer. Thank you very much for your attention. And
thank you, Dr. Tunkin. Now we invite questions.
Okay. Oh, thanks. Ilya, thanks for your presentation, very interesting, but I still didn't understand what is the mechanism of this process. Is it, in any case, in my opinion, it or not? Let's say this is a question. Is it a thermal activation of some chemical reaction? Which one? Is it thermal decomposition or it's synthesis of different components? Still it's unclear for me.
thank you very much for your question, Professor Veika. It's a very important question, important things, mechanism of this process. In our case, in case of deposition from copper and nickel and so on, it's thermal decomposition of salt in, and also reduction of this metal from copper, for example, copper 2 plus for copper 0. In case of silver or, for example, aurum, which we use photo decompositionable solution, is photo mechanism in this process.
Photo means at the same wavelength, because photo mechanism, photochemical mechanism needs some energy of photons.
No, of course you are right. For photo decomposition, we should find best wavelength which with complex with will collect energy. Yes, but in case of our solution, it's just thermal heating and locally selective thermal decomposition of and reduction in case of copper and nickel.
Okay, still.
Thank you. And we have time for maybe one more question.
May I ask a question? Can you compare the rate of deposition in your case and in case of electrochemistry?
Yeah, of course we compare. Thank you for your question. In case of electrochemical deposition, we can faster create some layer, some thin film on the surface of different substrates. But in case of laser deposition, we can fabricate selective small line, and it's more precisable in this case. But
there is laser-controlled electrochemical deposition, so
it's controlled and as a laser, and also controlled by chemical composition, because it depends on the components.
Right.
I think Vitaly Ivanovich means that it's possible to combine electrochemical and laser methods.
Yeah, of course it's possible to combine. I know these papers about combination, some like electrode and laser source for increase that this process. But in our case, it's just one-step process.
But as far as I remember, in this case, millimeters per second were obtained, deposition rates. Millimeters per second.
It's in case of CV laser, it's approximately 1 millimeter per second. In case of picosecond infrared laser, it's more than 5 and even 10 millimeter per second. It's quite enough for application and for fabrication of some devices, sensors, and so on.
I'm sorry, could you compare the results of deposition by picosecond or any pulse laser and continuous wave?
I think it's, of course I can compare, but it's after one presentation will be talk Dr. Sinyov, and maybe he can discuss more detail about nanosecond deposition.
Okay, thanks.
Thank you for the discussion. Let's thank Dr. Tunkin again.
And I'm glad to introduce our second speaker. It's Dr. Akhrimchuk from Prokhorov General Physics Institute of Russian Academy of Science. Dr. Akhrimchuk, please.
Thank you for introduction. So, good morning, ladies and gentlemen. Today's my talk is direct laser writing of helical break grating in vortex fiber. It's some kind of pioneer work of writing helical gratings in the fiber. First of all, short outlook of my talk. First of all, of course, about motivation, then a few words about couplet mode theory in helical break grating. Then I talk about experimental results, so writing and characterization of helical grating, and final conclusions. First of all, a few words about what is the vortex beam. Vortex beam, or beam that can carry orbital angular momentum, takes great attention last years. In contrast to the usual Gaussian beam, which have flat wavefront, vortex beam have helical front, as shown in the figure. It can carry orbital angular momentum. So along with spin, which is polarization, it can orbital angular momentum. And now our previous work was devoted to the writing of helical grating in the Yak crystal. For such grating, we have derived some phase matching condition. It's usually a famous phase matching condition, which is written on the green font by black letters. But when we try to write grating in glass, we meet difficulties. It is dealing with that we cannot write uniform refractivity change along the helix. So on the right, for example, So here you show case for the crystal, and here it is in the glass. So to proper describe phase matching condition for such kind, not ideal writing, we introduce to the refractive heat exchange this additional red part. And in this case, we get new phase matching condition for low conservation of orbital angular momentum. So we have added these red terms. So M here is the harmonics of the in modulation of refractive heat exchange along the grating. In order to write grating with constant thickness along the azimuthal angle, we applied beam shaper. Basically, our experimental setup is common for direct laser writing with 50-second laser pulses. But additionally, it has a spectroscopic slit in front of the objective, which reduces size of the beam. If you try to write helical structure with usual Gaussian beam, which have cigar-like beam waist, you do not obtain constant thickness of the helix. On the left, on the right, you see it is thinner than the up and down. And then to get the uniform thickness, we applied, as I said, spectroscopic slit, which reduces size of the beam in one direction. And in this case, we got constant helix with constant thickness, radial angular thickness. Radial thickness, yes. Parameter of beam waist is shown on the slide. First of all, before writing grating in the fiber, we tried to write grating in the bulk glass doped with germanium. So in order to obtain the proper pulse, to get proper pulse energy and overlap laser pulses. So we investigated the writing changing these two parameters, laser pulse, energy of laser pulse and overlap laser pulses. We found that in this type of glass, there are two modification thresholds for energy. Above one first threshold, we got positive refractive heat exchange, and above the second threshold, negative refractive heat exchange. And writing is rather smoother with, in the first regime, with positive refractive heat exchange. On the slide, you see the second regime with negative refractive exchange, and you see rather inhomogeneous writing. So in our experiment with writing in the fiber, we used the first regime with rather smaller energy and not large overlap laser pulses. And the refractive exchange is about 10 to minus 2, 10 to minus 4. Grating was written in the homemade fiber, which was drawn in the Fiber Optics Research Center. So this is a ring core fiber, which is called also vortex fiber, because aging most of this fiber, you can present these modes, gene modes of this fiber as vortex modes, so modes that carry certain orbital angular momentum. Basically, there are these modes can be presented or as superposition of usual vector modes, cylindrical vector modes, as shown on the slide. So, in order to write in the bulk, inside the fiber, we used common immersion technique. Fiber was in the immersion liquid and covered by cover glass. And in order to position beam waist exactly in the fiber core, we used luminescence of germanium oxygen deficiency center. So this center present only in the core and not in the cladding. And this very bright luminescence help us to position beam waist exactly in the core. Experimental setup for characterization of the grating. We use semiconductor tunable single frequency laser, and in order to optimize coupling of the beam to the ring fiber, we use hexagon, which form basal beam. Then we, in the focus of lens L2, we get a ring shaped waist, and then we transform this beam waist with reduction of size to the end or input end of the fiber. So we investigated as transmission spectra and reflection spectra by this photodiode placed here, or we can monitor images in the far field or for the reflected from mode in beam from the grating. I should note that except for the reflection for the grating, we have reflection from Fresnel reflection from the fiber end, and so really we have interference pattern between remote reflector from the grating and laser beam reflected from the end. And this helps us to identify vortex present in the beam. So here it is reflection and transmittance spectra. You see that we got multiple peaks in the spectra, which, each peak corresponds to different interference pattern. And we interpreted it as beam which carry a different orbital angular momentum in accordance with new conservation law which we have derived in the first slides. I would like to stress that in the case if there are no modulation in the along the helical track, which depends on the azimuthal length, we should have only one. M should be 0, and we should have only one resonance. But we see different multiple resonances in the reflector spectrum, and it could be explained if we take into account this modulation refractive index along the helical path, so which depends on the azimuth. So that's all. So the reclassification is a promising technique for formation of helical grating that generate optical vortices or change orbital angular momentum of fiber modes. And we have obtained generalized formula of angular phase matching condition of modes coupled in helical grating. It takes account azimuthal modulation, the refractive index change along the helical track. Thank you for your attention.
Let's thank speaker. Now our session open for question. Please. Yes.
Yes, thank you. Well, I might deep into the question. Thank you for the presentation. I understand that there are some interference methods that are used in this area. I also understand that they might not be quite as applicable here for your specific tasks.
Sorry,
Are there any other types of techniques that might be used to perform this task, perform this grading, and could you give us a comparison between your method and others?
So it's a very good question. I consider that the only way to write such equation is direct laser writing. It is this unique technique which can be used 3D fabrication. I couldn't imagine another technique.
Yes, all right, thank you. That's what I thought. Thank you.
Any question? I have a small question. What about its speed? Speed of this process? Yeah. And how many gradients?
Because of mechanical properties of the table, there are 1 turn for seconds. They're rather slow, really. But it is restricted by mechanical properties of the AIRON.TV table.
Thank you very much. And anything questions? If not, let's thank speaker again. And I want to invite for presentation Dr. Sinyov from ITMO University with title of his presentation, Direct Writing of Conducting Patterns with Pulse Near Infrared Laser Irradiation of Deep Eutectic Solvents. You have 12 minutes.
Great. Thank you. Thank you. It's a pleasure being here. I'm thankful for the opportunity to share with you our results. I will proceed with the topic that's been set in the first talk in our session, and I would give you some technical key issues in our work that has been done by 2 research groups, one in ITMO University and our collaborators, friends, and co-workers from Institute of Chemistry at St. Petersburg State University. And to give you a broader context here, I would proceed with some statistics. We all know that the global electronics market is a huge market, and it grows every year. And the Russian market of the electronic production and usage, it's not that big, but it has its own small but fair share. And there is a strategy for the development of the Russian electronics industry, which demands the increase in the domestic production and the domestic usage of the electronics in all the production areas. Unfortunately, it was issued right before the COVID-19 pandemic, so reality checks, but still it's a valid federal document. And we all know that despite all the demand, the global market of electronic production is a critical area, and it's been in crisis for the last couple of years because of the pandemics, because of the logistical failures, and so on. And some of the issues in this area, they are inherited from the lithographic method, which are deeply rooted in the production of microelectronics. And photolithography is a great technique. It's powerful, and it's precise, and it's mature, but it is also not simple enough, not eco-friendly enough, not cheap enough, and not flexible enough. And these issues might be addressed if we use some hybrid methods, maybe implement some of the benefits and use some benefits of the direct laser writing techniques. And the solution here might appear, well, in the form of, sorry, not that, sorry, pressed the link, sorry. So the solution here might appear in a form of solution, meaning the, for example, deep eutectic solvents, which were introduced earlier today, and we all already know that these are the state-of-art metal-organic inks, which provide the metallization of the surfaces with high effectiveness because of the high concentrations of the metallic salts, and they are easy to work with. They have convenient production temperatures. There have been some recent advances using the water-based solutions and some other metal-organic inks, but these are the new wave, new era in this area. The main issue, the key issue, as it's been already stated, are the production rates there, which are usually limited by the hundreds of microns per second, maybe a millimeter or 2 per second, which brings us to the point of our own research. In our research, we take a leap there, and we try to push the limits there. We use only the commercially grade laser processing complex, and we use it to test some approaches to enhance the production speeds. We started simple with these elemental circuits like basic lines, and then we have proceeded with something more complex, some of the structures of arbitrary shape. Here are our here are our materials. There have been more, but these were found to be most effective ones, and all the main results, all the further results were were achieved on the solution based on the tartaric acid and copper acetate. Now back to our production technique. We have developed 3 very simple techniques to enhance the productivity of this method. First of all, we have implemented the laser-induced microplasma treatment of the acceptor substrate to form the preliminary surface roughness, to give to boost the deposition speeds of the copper, and also the residuals from the target. They stay on the acceptor substrate, they increase the absorption there, and they serve as a sacrificial layer, effectively raising up the effectiveness of the deposition process. Second of all, we have proposed to use the auxiliary substrate, just a basic cover glass, which we place on the top of the desk, just as simple as that, and that significantly boosts the productivity. Here our results. The main point here is to localize the desk, which stays there in a liquid form, quasi-liquid form, to localize it in the laser heating spot, and this cover glass helps with that by using its own surface tension, which gives us great results. Second of all, we have found useful to treat the sample by the multiple times, multiple exposures, using the initial sediments from the copper as a seedlings for the copper layer growth. Using this technique, we can speed up the process. We have done it up to the 55 millimeters per second, and the recording of the conductive circuits was done by the 8 consecutive exposures, giving us the effective speed of up to 6.5 millimeters per second, which is not the limit here. We can do more. These approaches, these simple techniques, has allowed us to map the processing areas here. The highlighted area is fully conductive, and we have described the temperature dynamics here. We show now, we understand now that this probably is the temperature-related process, and the solution needs some time and some effective temperature to be heated to start and to fully go into the deposition procedure. Both EDX and XRD research show us that our tracks are consistent of the metallic copper, which is great for us, and the resistivity tests show very promising results. Yes, we can't compete with pure copper itself, probably because of the porosity. We exceed the resistivity here by the order of magnitude, but we are close to the numbers that are given by the electrochemical copper deposition, and we are far better than laser chemical, than LCVD deposition and some other similar researches. Using these techniques, we can successfully go into creating, to direct writing the circuits and coatings of all the arbitrary shapes. These are fully conductive circuits. And also there is one more result that I would like to share with you, which is quite interesting. In some narrow regimes we have found the laser-induced periodic surface structures formation here directly on the deposited copper layer. Lips, apparently they have formed directly during the procedure of the deposition. And this might be promising, this might be important, firstly because there are some results showing the better solderability of the contacts when they are covered with lips. And also we've heard yesterday the results from the Dr. Shuleika, who told us about the electrical anisotropy in the lips treated areas on the amorphous silicon. So it might be the future of tailoring the conductive circuits on the integral schemes. In conclusion, we have developed simple technological approaches which boost the productivity of the method, and we are using them to switch to the polymer materials to give us the possibility of creation the integrated circuits and flexible electronics for the wearable sensors and so on. Thank you very much for your attention.
Yeah, let's thank the speaker. Yeah, our section is open for questions, please. Yep.
So, okay, thanks Dmitry for very interesting talk. I have no objections about the methods, but I have do something about the results. The first question is, do you like to produce conductive or resistive lines?
Well, conductive, of course.
Conductive.
Conductive, yes.
I think so, because when somebody like to produce resistive lines, one should take another materials like chromium, like nickel, like and so on. But when people use copper, then like to produce conductive. But when we compare the conductivity, not resistivity of the lines, the conductivity is significantly less than, for example, when people receive such copper, I mean specific conductivity, сопротивление на квадрат, или проводимость на квадрат. When people use, for example, electrochemical or other methods to produce such lines. What it's a question.
If I understand correctly, this is the question based on this particular slide, and yes, I understand that it would be better to measure the conductivity here. I agree with you. It would be more easy, yes, to compare. We will try to switch to the conductivity measuring. Thank you for that. The resistivity here was based on the research of simple tracks, simple lines, and we have measured only simple lines here for the resistive properties. And I feel like it would be better to create the circuits of the necessary shape and then to measure their conductivity. So we will do that after we will close on this topic.
Thanks. Sorry, the slide number 12. A very small question. Number 12.
Slide number, I'm sorry,
12.
thank you.
12. Such a green points, it's probably oxides, copper oxides, yes?
Here, yes, probably. Or it might be residuals from the DES. I'm not quite sure here. It also might be the residual from the titanium, some titanium oxides that have left from the pre-treatment of the substrate. But on the other hand, here we have beautiful and clear copper structures.
Excuse me, maybe I wasn't careful, but what was the thickness of the films you obtained, and what was the cross-section of this film? How uniform they were?
Here we have the Here we have the average thickness of the no, this is the width. Sorry, I don't have these results on me, but we have done some profilometry there, and the thickness of the layer is about 1 micron with
Excuse me, can you use microphone, please?
When you produce thick film, then deposition rate is 1. If you produce thin film, then another deposition rate. And you give deposition rate always, but not with thickness.
If I understand it correctly, that you're asking about the thickness of the films and their relation with the deposition process, and maybe with the relation to the effective conductivity there. These are valid points, these are valid questions, because the uniformity of these tracks, well, it bothered me. It bothers me a lot, because the effective conductivity is not the same as the local conductivity.
They don't look uniform.
Well, right, maybe not these ones, but this one is better, and this one is definitely better.
Excuse me, colleague, we have no time for questions. Let's thank speaker again, and we can discuss during coffee break and dinner. And I want to invite for presentation Syed Gazov. Absent? No? And not online? No. Maybe here is online. Can we try in just Professor Nagamov? No. No. Huh? Very sad. Let's move further. I want to invite next presentation Anna Libovka from Tomsk Polytechnic University with presentation entitled Laser-Assisted Design of a Graphene Glass Conductive Surface for Electronic and Sensing. Please, you have 12 minutes.
Thank you for introducing. Good afternoon, dear colleagues. I'm very glad to see you all here. And I'm going to present the work which was mostly done in Tomsk Polytechnic University in collaboration with the colleagues from Germany and China. And my talk is dedicated to the fabrication of, thank you, yes, much better, graphene glass composites using the laser-assisted methods. The motivation to do this work at all is connected to the need now in modern electronics and optoelectronics to make a lightweight and compact device, and especially they have to be compatible with different conventional surfaces which we use in everyday life. It could be polymers, it could be textiles, and glass, which I'm focused in this work. There are already several ways how to make it conductive, including the metal and metal oxide coatings, coatings with carbon nanomaterials like graphene or CNTs, or conducting polymer coatings, for example, like PMMA. But these are still coatings, and they are not very mechanically resilient. That could be scratched, that could be removed, and so it could cut the lifetime of the sensor or the device. So the question is how to make the combination more robust, how to make the lifetime longer. And the obvious answer is to make a composite. And there are already several ways how to make it, for example, using bulk technology, like the solution mixing, when we include the filler, for example, carbon filler to the glass in liquid, and after that we make the composite. But actually, for the sensors, for electronic devices, we don't need the whole surface to be conductive. We don't need it all to be modified. What we need is just to make the surface modification. And that is exactly what we are doing in our group for about 5 years. We are developing the laser-induced integration, mostly to polymers, following only the modification of the top layer. We are using the already prepared polymers. After that, we are making on the top of it the film based on nanomaterials, and we made a direct patterning from the top. And these are several works which were done following the same technology. For example, we made the integration of reduced graphene oxide to polyethylene terephthalate for the fabrication of ECG monitoring bioelectrodes. After that, we performed the integration of graphene modified with diazonium salts, following the same route for the multi-sensing platform. And on one of the latest work, we performed the integration of metal nanoparticles. First, it was only aluminum. After that, it was spread to other metals, to the surface also of polymer. But what combines all these works is the integration was to polymers. And for glass, this approach could be not that straightforward, and because of the substrate itself. And, but it doesn't matter that we can't use the laser-assisted methods to make the composite like this. We slightly changed the technology. What we did is the following. We used PET substrate, we covered it with graphene oxide, and we put the glass on the top of it. And using this graphene oxide sandwich, we made the irradiation from the top of the glass. And the processes that are happening behind are presented here. The laser irradiation of the visible range is coming through the glass, focuses on graphene oxide, and performs the laser-induced graphene reduction. And after that, the reduced graphene oxide is going on top and integrates to the glass. This concept is, it looks so easy and so, I don't know, repeatable. And that is what we get at the end. We have a very highly conductive composite. The sheet resistance is about 190 ohms per square, and it is also the best quality RGO, which I will comment a bit later. This integration is robust. We checked it with the scratching, with mechanical scratching, with ultrasonication, and we didn't lose the electrical performance after that. And of course, it is specially confined. We don't need to modify the whole glass. We modify only the patterns that we are interested in. And recently, this idea got so interested to scientific community that 2 weeks ago it was published in Advanced Materials. So I'm very happy to present a quite fresh work from our team. And now we'll elaborate a bit more on the processes behind. I already mentioned that we have a very good quality RGO, and that is not very typical because the laser reduction of graphene oxide is a very common method. It was published since 2009 or something. But if you take a look on the red spectrum presented here, you could see that all peaks, DJ and 2D peaks, are very sharp, and especially it is not typical for 2D peak. For graphene oxide, the typical width of the peak, if you talk about numbers, is about 120 or 140. And for reduced graphene oxide, the chemically reduced graphene oxide, it's about 90, and here we have 60. You could also compare the spectrum to the graphene, CVD graphene, which was placed on the tops of the silicon substrate. And we could see that the quality is very good. And we attribute to the LIPT process itself. I mean, what we have here, when we have the reduction in our very limited, in terms of space system, the more beneficial, energetically beneficial way for graphene oxide, only for the lightest particles to go up. I mean, so the only best reduced graphene oxide without oxygen groups goes on top, and that is why what we have integrated is a very good quality graphene. But also on the right side, you can see that not only graphene is presented in this spectra, there are also some regions rich of silicon. And these spectra are mutually exclusive. So in the areas where we can see the silicon peaks, you barely see any graphene. And I will also comment a bit on the next image. And here what we also need to see is that we still have the D band because of the wrinkles that we could see from IFM image, but the initial graphene oxide already has the wrinkles, so that is fine for the system. These are the same images obtained on our composite, and what we could see here also confirms our Raman observations. There are some areas rich of sodium, which are obviously coming from glass sites. We see the carbon distributed almost everywhere, and some regions rich with silicon. And also you could see the cross-section with RGO parts and some pores formation, and the thickness of the composite normally varies from 20 to 30 micrometers. So what is to see what is happening, and from where we have silicon, we performed some XPS spectra. Some results are quite expected. So we have, after irradiation, we have the rise of carbon content. Comparing to pristine glass, after radiation, we have changes in the silicon region. We have silicon in 2 chemical states before, and after that we have only CO2 after laser radiation. And if we take a look on the carbon region, we also see the huge rise in intensity of carbon bonds, CC bonds, and with some leftovers with oxygen, which is also connected to the glass. And what is happening in the system? We have the oxygen depletion, and which raises the appearance of sealants, which decompose to silicon and hydrogen, and the hydrogen-rich environment promotes the appearance of new silanes. And we have the silicon oxide, which combines with the carbon to form silicon carbide and CO. But one could notice that if you are mentioning the silicon carbide, why don't we see it in the XPS spectra? But that is not completely true. If you remember the system, we have a graphene oxide sandwich. And what I show in left side is the glass part. And here we have the second part with the PET part. And here in the silicon region, we could already notice that we have some silicon carbide here. And also the silicon carbide combines with silicon oxide to make some silicon domains and release of CO. Also, to see what is happening in real time while fabrication our device, we made a high-speed video recording of the process. And you could see some kind of heart beating in there that is related to the melting and cooling of the system caused because of the pulsed radiation and because of the temperature gradient in the system. And to see what is happening, we also performed the modeling of the temperature increase simulations, following the same parameters that we used for the real samples and in real experiments. And we could see the huge temperature rise within the first 0.9 seconds and cooling down after that. I will not talk a lot about applications yet, but still I want to mention some that we already did on our samples. We also could functionalize our materials for sensing purposes with silver. For example, in this case, we made the deposition, electrochemical deposition of silver on the top of our composite. And you could see the distribution of silver on the EDX mapping. And we use this material for two types of sensors. One electrochemical sensor, and the second one is optical SR sensor. We use the model Analyte for NBT. And we also got kind of very good results with the limit of detection for electrochemical sensing. And we saw the conversion of NBT to 4ABT in SERS. And the last application I want to mention is the electrothermal heater, which allow to reach the temperatures up to 330 degrees, and also we checked it continuous operating for 2 days with the less temperatures of 120 degrees. At the end, what I wanted to remember, that laser-assisted technology allow us to make in a very easy way a very highly robust and highly electrically conductive composites. And the graphene that we obtain is very, very good quality. And this material could be used in various applications, and also we could make some functionalization, not only with silver, with other metals. And varying the laser parameters, we could also change the conductivity in a wide range. I want to say thanks to RFBI funding, and of course to all my group, to TPU, for making this research possible. Thank you.
Let's thank speaker. And now our session open for questions.
May I have a question? May I ask a question?
Yeah.
You work in big collaboration, and the question is, what is done in TOMS?
Use microphone, please.
It's very hard to hear.
You are working in a huge collaboration with other countries, and the question is, what is done in Tomsk?
In Tomsk, actually, almost everything, the concept itself, all the samples, and the idea is coming actually originally from TPU.
What were the roles of the other collaborators?
We are working on the joint grant with RFBI DFG with Germany. They perform the characterization and help with the interpretation of the results, because we have, I presented only a part, we have quite a lot of results so, in our paper, so we had job for everybody.
Are you still with them?
I don't know, like now we are still working on our next paper with this grant. This year we are still working together. That is the last year of this grant.
Thank you. Thank you.
Okay.
Any questions?
May I ask?
Yeah, of course.
Put please slide number 1 or 2 with a scheme of lift.
This one.
Okay. First question. In your case, the GO should absorb the radiation, yes?
Yes.
And when it goes, when it's deposited on the glass, how thick should be the layers of the graphene?
I'm sorry, what, how what?
How thick?
How thick?
Насколько толст?
The thickness of the composite we could see here.
No, simply say me.
On,
Okay, I will say you my idea. When it becomes more thicker, it should absorb the radiation. Okay?
you mean the graphene oxide itself, yes?
I mean
The film of graphene oxide?
what is the composition of deposit on the glass? GO
Yes, that's
or
graphene
graphene.
oxide. Yes.
So it should absorb the radiation, and in this case it will be not back transfer but forward transfer in the opposite direction. Yes or not?
That is the whole experiment, the whole idea of the experiment was to make a back transfer exactly to have the lightest graphene on the top.
Okay, probably you didn't understand me. Okay, the next question. You every time you speak about reduction, but this experiment you make is in a normal atmosphere or in special.
No, these are the room conditions, except that the combination, the sandwich itself creates the low oxygen atmosphere, but otherwise everything else is normal.
Yeah, okay. So in your case, because of upper glass, you have low oxygen atmosphere.
Yes.
But reduction in where? In some atmosphere of products, or how? Reduction means opposite to oxidation, yes?
Yes, it means that we have the gas products from this reduction, and we remove the oxygen-containing groups from graphene oxide. So just happen this.
Okay, thanks.
Okay, let's thank the speaker again. And I'm glad to invite for presentation Professor Evgenia Sheremet from Tomsk Polytechnical University, and for presentation about laser processing mechanism of graphene oxide. Evgenia, you have 12 minutes.
Hello. First I should start by presenting what graphene oxide is. Graphene oxide is a sheet of the well-known material graphene, but with a bunch of different oxygen-containing groups attached to the sheet. As the result, the big share of the carbon atoms doesn't have the sp2 hybridization typical for graphene, but has sp3 hybridization. This material, unlike graphene, is transparent. It is brownish transparent. It's also not conductive, and it is dispersible in water, which makes it very convenient for solution processing. Further, it can be reduced either chemically using such chemicals as hydrazine or thermally. The very typical way to do it is using heating in the oven between 200 and 400 degrees Celsius. As a result, the oxygen-containing groups get removed from the surface and the graphene sheet is partially recovered. It's not ever fully recovered, therefore the recovered material is called reduced graphene oxide. And obviously, except for the oven, one could use flash lamp or a laser to perform the same. The laser process is particularly interesting because we can localize the effect, and it's also environmentally friendly compared, for example, with chemical reduction processes that require toxic chemicals. What we have been doing for several years now is looking into using these processes to create flexible electronic materials, in particular aiming at flexible wearable electronics. And the first achievement, the first breakthrough, I would call the ECG electrode. In this case, we used graphene oxide from a dispersion, deposited on a polymer substrate, and then reduced with the laser. This surface was used as a surface of the ECG bioelectrode, and the electrode performed, in terms of signal quality, this as good as commercially available silver-silver chloride electrodes. However, there are two crucial benefits of this electrode. First of all, they don't require the gel. When you have done ECG monitoring, you might have noticed that the silver-silver chloride electrode has electrolytic gel. This gel is necessary to create the environment where electrochemical reactions can happen, and therefore the ionic current of the body can interface with the electronic current in the electronic devices outside. This gel tends to dry up and cause irritation. Therefore, the normal use of silver-silver chloride electrodes is limited to just 24 to 48 hours, while we have been able to use this electrode for 4.5 days without any visible issues in terms of performance or in terms of irritation. And this is, of course, governed by the process of the reduction of graphene oxide. And the mechanism itself, when it comes to thermal reduction, is quite well described. When heating up the graphene oxide up to 100 degrees, first thing that happens is the removal of the water. Water, due to hydrophilicity of graphene oxide, water is trapped in between the graphene layers, and upon heating, it is released. Further, the reduction or the removal of the oxygen-containing groups happens in the region between 150 and 300 degrees Celsius, and upon further heating, around 500 degrees in air, the material would burn. And this mechanism, when it comes to laser, is then not so straightforward in the sense that we must consider whether the photochemical reactions happen or the photothermal reactions. And there are evidences to both. The photochemical mechanism is understood as removal of epoxy and hydroxy functional groups upon absorption of the quantum of light, that is photon. And photothermal mechanism implies that there is a laser-induced transfer of energy to the lattice that in turn leads to the reduction of graphene oxide. But most papers actually argue that there is a combination of both mechanisms, with particular the paper by Van showing that, suggesting that the light absorption itself leads to the removal of the oxygen groups, while the heat leads to the conversion from sp3 to sp2 or the recovery of the graphene-like structure. Now, that is the first reason why we are looking at the mechanism of laser reduction of graphene oxide. The second reason is the process we have discovered in the recent years, that is the laser integration. And in particular, when we were working on the material diazonium functionalized graphene, that is graphene functionalized by these diazonium organic groups that can then be removed analogously to graphene oxide with the recovery of the conductivity. What we have observed in high-speed imaging and also from other evidence is that there is a melting of the polymer upon absorption of laser light by graphene that then transfers the heat to the polymer, melts it, and the material mixes, locally forming the composite. This composite shows interesting properties in terms that it can be scratched or bent thousands of times. It's also chemically inert, considering that we are using such polymer as polyethylene terephthalate that's quite stable, and carbon itself is also a very chemical stable compound. So this material feels itself quite well in biological media, in different environments, including biological or corrosive media. And the issue is, of course, again, that we are facing that this process is not entirely understood. So what we have started doing is developing a model that would allow us to first understand what is the temperature in this process when induced by the laser, and then we expect it will lead us to understanding or to assigning the mechanism of the laser reduction. What you see here is the film of graphene oxide on glass deposited by deep coating and a finite element method simulation of the temperature by a laser spot of 4 micron. And we can see that the temperatures in this case can reach, depending on the laser power, up to several hundred degrees. To verify it experimentally, we have used Raman thermometry using silicon nanowires that have been deposited on the film and then radiated by the laser Following the shift of the Raman peak, we can deduce the temperature of the nanowire and its environment to some degree from the shift of the Raman peak. And this is the obtained dependence of the temperature on the laser power. Now to match it with the understanding of the graphene oxide reduction, we have been using the monitoring of using Raman spectroscopy. And one of the effects that is not reported in the literature, but we have reproduced it multiple times, is the reduction of the photoluminescence background upon reduction. And it has a gradual effect depending on the power. So when we look at this and see the behavior using different lasers, we can tentatively assign the areas where different temperature regions occur. So this blue region corresponds to the low temperature heating up to 100 degrees or the water evaporation regime. And then these regions would then correspond to the reduction regime. We can also see that different lasers give the behavior that is indeed very similar, and that points us in the direction that this is a thermal or photothermal mechanism first and foremost. That's consistent with the hypothesis that are expressed in the literature that the photochemical mechanism would dominate in the ultraviolet regime when the energy of the photon is enough to trigger the chemical reactions. In conclusion, I would like to point out that there is a debate on the mechanism of the laser reduction of graphene oxide, and our own results also push us to understand the mechanisms of the laser-induced heating in the system. The modal and the experimental results show reasonable agreement on the temperature evaluation. We have also observed the photoluminescence background that is particularly fast, decreasing particularly fast in the region of the water removal. And then we see a further reduction in the reduction region. We can see that using different wavelengths of the laser, the behavior of the Raman spectra is similar, and it points to the dominance of the thermal mechanism that is also consistent with the literature. However, this is not the typical way to investigate the degree of graphene oxide reduction. So in further work, we plan to perform atomic force microscopy, CS AFM, and also refine the model. And we hope that that gives us the definite answer on the mechanism. Thank you.
Let's thank speaker. And now our session open for question. Yes, please.
May I ask?
Thank you for a very interesting talk. As far as I understand, your final goal is to obtain pure graphene, but it is not possible for some reason. Is it so?
I'm sorry.
Sorry.
What?
So ideally, it should be to obtain pure graphene, yes? But you obtain graphene oxide.
We obtain reduced graphene oxide. It has a high degree of defects, unlike what, for example, Anya has shown, where she showed the high quality graphene. But that is not really the goal. The thing is that when we are looking, for example, at the RGO bioelectrodes, we must have electrochemical reactions on the surface. So we think, which is something we are investigating also now, that if we have a perfectly reduced graphene, it will not work as well as the bioelectrode, so it will not form the proper interface with the human body. But that is something that's a hypothesis.
Okay.
Next question,
I have
please.
a question. First, thanks for a very clear presentation. And question mine is very small. Which laser did you use for experiments?
Thank you.
Maybe I missed.
We used, in this case, in the case where I showed the fabrication, we used 405 or 450 microsecond laser diodes with microsecond pulses. But for the Raman experiments, we used continuous lasers, and the reduction was performed up to 60 seconds. Sorry.
Thanks.
Okay, may I ask some question? Thank you very much for interesting talk. And I remember one paper, maybe in some Nature journal, when people look on the film of reduced graphene oxide, they observe some stochastic process, some islands over the surface of this film. You have stochastic reduction and oxidation, so you can see some stochastic migration of luminescent spots over the surface. Do you observe such effect, and how you take into account this process in your experiment?
Yes, indeed, there are works that show that the groups migrate over the surface and the structure partially recovers. For example, there can be kind of the formation of the graphene areas inside that film, but that is not something we have investigated.
Okay, thank you. Thank you very much.
And we have time for a last question from Lev, please.
Thank you very much for an interesting talk. I have a question about the thermal modeling which you carry out, and you have a very unstable situation when the spectrum of absorption are changing dramatically due to the first step of your irradiation. How you take it into account, such reasons?
That's a very good question. That's something we are not taking into account yet. Right now we are using the heat source, and then the heat source that is available in the COMSOL software does not allow us to take into account directly the change in the optical absorption. So we will have to kind of add it manually, but yes, obviously it will have an effect, which is, I think, maybe also the reason why we have here the change in the temperature versus power. That is exactly where the reduction starts happening, and then we have the change in the temperature that is achieved.
Yes, but here you applied the Raman technique of the measurements of the temperature, but again, did you take into account that the silicon nanovirus are also heating by the Raman irradiation?
They are, but the benefit of the nanovirus is we are using the irradiation for 60, in the measurements we are using 15-second measurements for 8 cycles, if I'm not mistaken, so that's quite a long measurement. So we expect that the thermal equilibrium is achieved considering the small size of the nanovirus.
Thanks a lot.
Okay, let's thank Evgenia.
Excuse me.
Sorry.
May I ask one more question?
Okay, some short question.
Yes, it's a question on a model. You see, you showed these videos, and what I see there is like hydrodynamics mixing of the melted, of the liquid. So the question is, have you considered hydrodynamics of the melt?
Okay, I need to point out that the model at the moment is only limited to thermal behavior. The hydrodynamics is something we hope to be able to address. The reason we are starting actually with the thermal behavior is that we thought the system was quite simple. That you can observe, if you observe the melting, all you need to know about the polymer is the melting temperature. So if you melt it, that's it, that explains everything. But no, it's not a predictor. We have tried multiple polymers and it doesn't predict the formation of the composite. So we have to go step by step and develop all the stages of the model, starting with the temperature.
Maybe I can help you to include hydrodynamics in your model.
That would be great. Let's talk about that after.
Okay, thank you again, and you can, of course, discuss later. And I'd like to invite our next speaker, and presentation will be online. And Dr. Ibragimova from Center of Advanced Technologies, Tashkent, Uzbekistan, and topic of drilling of micro-hole grids in quartz crystals with ultraviolet picosecond laser. You have 12 minutes for presentation, and you are welcome.
Good afternoon, dear colleagues. I am happy to see and hear you. So this is applied research. Our task was to use, to develop laser technology for drilling quartz or silicon glass matrix and make micro membranes for splitting liquid mixtures. So the laser is in structure techniques were in the center of advanced technologies, and all irradiation were done in the Institute of Nuclear Physics and some structure measurements as well. So laser beam interaction with the electric can be divided into several steps, starting from the single or multi-photon absorptions, very short, then avalanche ionization, somewhere here is the plasma generation, if the mode is proper. Then electron heating, material heating, then after 10 picosecond, the thermodynamics process, and finally photochemical processes which influence the chemical composition of laser effect area. The main problem in laser drilling of broad gap dielectrics are low coefficients of laser beam absorption from UV to middle infrared, both in single photon and multi-photon mechanism. Brittleness of quartz crystals, glasses, and low thermal conductance. So the technologies are based on melting evaporation mode, then at low intensity of laser. Then at high intensity, with ablation mode, with plasma ignition. Then to increase the absorption, people use silicon oxide with admixtures to have absorption in the gap. Applying metal films reflecting the laser beam from the opposite surface. Using laser with high repetition frequency, remove heat with water flow, etching some area around drilled holes and make the cylinder profile. Our approach to solve some of these problems are to use cobalt-60 irradiation so as to increase the conductivity, increase the absorption to higher saturation level. Also irradiate with 4 MeV electron beam to generate charge trapping defects. The absorbance against higher saturation is effective. Then choose the ablation mode with powerful UV picosecond laser, and the recommended average energy of pulse about 10 millijoule, which is capable of igniting plasma when it is focused on the surface. Pulse repetition was not high, from 20 to 50 Hz, and we compare the efficiency of drilling holes in silicon oxide glass with high concentration of OH, let's say wet glass, and alkali silica glass which are more mechanically stronger than pure silica, and to see where the quality of microscale filters will be better. So our results, we irradiated and first measured the optical absorption and infrared. You can see the very intensive absorbance, but at the maximal absorbance comes to the fourth harmonic of laser, 255 nanometers. Infrared of wet CO2 glass has a lot of intensive absorption bands, which provides the effective heating of lattice. Element and phase transformation after the intensive cobalt-60 other irradiation. You can see here. We found phase transformation, which is shown here. Is before irradiation. You can see the network size about 1-2 nanometer, and also the already selective nanocrystals with selective peaks, which we had to identify. So in the network of glass, we can see crystal silicon oxide and also silicon oxide hydride phase here. After irradiation, the oxide structure changed from cristobalite to tridimide, and instead of this phase, we found fluorine silicon hydride. Fluorine could come only because of nuclear reaction, and we suggested that maybe silicon can split into fluorine and tritium, or and then the neighboring oxygen can trap the tritium and transform to the fluorine. And also oxygen itself, with such heavy irradiation to 6 farad, can split into 4 helium nuclei. This is set up. This is a Lithuanian produced laser, picosecond, giving 4 harmonics exit windows. Here with China automatic target transmissions XYZ with a step to 10 micron. This is a lens to focus 7.5 nanometers or millimeters, so as to make this grid. Here are scanning electron microscope and local element analysis with EDS system. After drilling with the 4 harmonic of yttrium garnet laser. The central hole you can see here, 20-30 microns, then it's surrounded with shock wave on the distance of 100 microns, and we checked the local element analysis over this surrounding area, and we found also fluorine appearance and changing of stoichiometric ratio of silicon and oxygen. And silicon decreasing, oxygen some oxygen also. At higher energy of laser, within 5 and 10 millijoule, we could increase the diameter of hole, the area of damage with shock waves, and increase in concentration of fluorine and a lot of oxygen, or increasing of silicon, which is just normalized to 100%. So if to calculate the geometry of the focal area, we could vary the theoretical limit of laser drill holes at the 4th mode, about 5 microns, but actually it was higher, but there were very small holes aside. You can see here about 1 micron or even less, which could be due to higher mode, higher harmonic generation. Here is the surface coated with a tiny silver, and you can see conical shape of this silver. And after drilling, we put the silver to see better in microscope this dielectric surface. And you can see here this drilled area around the preliminary to drilling the first pumps. makes like a polishing of the surface surface, and this is after drilling. And this is part of evaporated or melted system. Here are the radial distribution of concentration of carbon, oxygen, silicon, which was found on the surface of quartz, and also this multi-component sodium alkali glass. The absorption spectra showed very effective, intensive absorption in the area of fourth harmonic, and here we could measure the size of nanoparticles grown due to irradiation, both in gamma and cobalt-60 and 4 MeV electron beam. The sizes of nanophase increased from 10 to 30 micron. It could be estimated both from XRD and from optical absorption spectra. This is alkali silica glass drilled at 5 millijoule. You can see another area of damaged with shock waves. Far away from the hole, the composition is here, and after months or 2 months, because of relaxation of glass, which is viscose, this area was changed, and the hole diameter increased about 50%, it became wider. And here are the deformed to ellipse smaller holes aside due to high harmonics. We found the maximal irradiated area and found what happens with the content. We see 16% of fluorine, which could come from a nuclear reaction induced both by irradiation or just by UV laser exposure. Here you can see the ratio between crystal phases, silicon oxide, cristobalite or tridimide, and sodium aluminum silicate, and also separate phase of aluminum fluorine 3. Here is an example of barium heavy glass, where we also see the change of phase composition. Here are our drilled grids in quartz.
Excuse me, you have one minute.
Yes, I'm finished. And here is a glass which are more damaged than in case of quartz. So this is the estimation of the amount of material evaporated, ablated from the holes. So we could make hole diameters from 5 to 50 micron with interval of the diameter which are in demand for splitting or cleaning, filtering water from oil, for example, in milk production. So the mechanism are known for femtosecond and picosecond pulse. But I would add here, instead of or after avalanche, the plasma generation, which took part in this mode of grid drilling, and result in the observed change in composition, element composition. Our result are here, what we could see: shock waves, structure phase transformation, no new chemical elements, and we also measured annihilation peaks, which from laser plasma, which is indicative of nuclear excitation, electron-positron pairs, which during annihilation give rise to this peak. So thank you very much.
Thank you very much. Let's thank speaker. And we have time for, only for one question.
Thank you for interesting talk. Does nuclear reaction and laser excitation, is it at the same time or it is separated in the time? So nuclear excitation and laser excitation, is it simultaneous process?
Oh, please repeat again, because
I did not understand. Nuclear excitation, and
nuclear excitation.
It is before laser excitation, or it is simultaneous?
Okay. So we made two experiments. At first, we saw what happens without the effect of laser. What happens with after heavy irradiation, and we found this change of composition that we could not measure in the beam, in gamma, in cobalt 60 or electron beam. We could not measure. But after igniting plasma during drilling holes with the forced harmonic, we could put detector aside and measure this annihilation peak, which is indicative of possible nuclear reaction of the excitation. And we also saw fluorine production and fluorine phases, which could originate from nuclear reaction. We compare to laser effect and nuclear radiation.
Okay, thank you. Let's thank speaker once again. And I'd like to invite our last presentation for this section. It's Maxim Fatkulin from Tomsk Polytechnic University. It's Tomsk. And topic of his presentation is laser processing as an approach for an inexpensive green and scalable dual channel pesticide sensor fabrication. Please, you have 12 minutes, Maxim.
Thank you. Once again, my name is Maxim Fatkulin, and I'm the second year PhD student of Tomsk Polytechnic University. Today I would talk about laser processing again, because this is the approach we are working on in our group. So eventually, now there is a huge trend in the world to shift for the green methods of fabrication, to the green chemistry, to the green energy. So I would particularly stop on the green chemistry principles of which was summarized by American Chemical Society. One of them is a real-time analysis for pollution prevention. So this work is dedicated to this principle. Here in this work we are trying to implement laser processing as an approach to create new materials for highly sensitive and inexpensive and scalable fabrication of the sensing devices to monitor the pesticides residuals in water and in the food. So I would start a brief on the history, how we came to this. So last year we found an approach how to make a laser-induced composite between metal and polymer by the direct laser writing of the aluminum nanoparticle film deposited on the top of polyethylene terephthalate, and subsequently under the laser processing there is several processes undergoing. So first of all, the aluminum nanoparticles acts as a photothermal transducer. So during the radiation there is a huge temperature rise, and the polymer underneath that start melting. But still the temperature is increasing, so further temperature reaches the pyrolysis point, and there is a formation of the carbon network, which also interacts with the aluminum nanoparticles and creates the aluminum carbide shell around the nanoparticle itself and the conductive carbon network on the polymer surface. So eventually, by this we achieved the composite between metal, polymer and carbon. So we wondered if this approach could be scaled to another kinds of nanoparticles, and it does. So here in this work, we used the laser processing of the silver nanoparticles films deposited on the PET. The idea was that the silver nanoparticles itself are plasmonic, so they could open the window in applications in sensing. And we found the interesting thing that by controlling the laser power, we actually could control the process of composite formation. So here you could see the difference, even in the color by bare eyes, you could see the difference, that some of them are light brown and some of them are black. So eventually, light brown is just the integration of silver nanoparticles into polymer by its melting. So, but the black ones is the products of pyrolysis and mixing it with silver nanoparticles, as I was described before. So we achieved the plasmonic structures by this approach. And we implemented this material to fabricate a dual channel sensor, which ideally would allow us to monitor the pesticides by optical spectroscopy, in particular CERS, qualitatively, and make the quantitative analysis by electrochemistry. So the CERS part, I think everyone knows that to have enhancement in Raman spectroscopy, we need to have a spatially confined hotspots to have actually the enhancement. And analyzing the surface morphology obtained by scanning electron microscopy, we see that the particles are saved their shapes, but they are welded together. So eventually there is a partially integration into PET, and the other active surface is represented by the welded nanoparticles, which grows up on this. We investigated the process of formation, the laser-induced formation of the composite. So here in the video we could see how the process is going. That's what I was talking about the melting and pyrolysis. And the actual stages are represented in the pictures. Since we aim to create a CERS substrate, we make a model experience with the molecule of FONBT, which has a really good enhancement in CERS, and also because of the sulfur containing has a high affinity towards the silver. So here we could see the typical spectra from FONBT and even the partial photocatalytic conversion to the other state. Since we are actually trying to combine two techniques, is CERS and electrochemistry, we also checked on the model system that we could monitor the chemical reaction, the electrochemical reaction by Raman spectroscopy. Here you can see the potential-driven conversion of dimer-capped azobenzene to 4-amino benzotiol. But since the work is aimed to detect the pesticides, we shifted to pesticide itself. So as a first pesticide, we selected the sulfur-containing pesticides, since it would perfectly show if the substrate itself is suitable for the goals we are trying to achieve. And it does. In Raman spectroscopy, we see the spectrum of the pesticide, as far as I remember, even 50 times lower than the maximum allowed concentration. But these substrates fail to deliver the electrochemical sensing. Mostly, especially about this pesticide, because these pesticides have only oxidation peak located on the positive potentials, and the silver also got oxidized in positive potential, it loses its properties. So we came back to another of the previous results on laser processing. There we already shown the good electrochemical sensing performance. As Anna already mentioned today this approach, so we tried to implement the composite between the modified graphene oxide with diazonium salts and PET also. This composite is obtained the same by direct laser processing of the films, and make the electrochemical detection on this material. We achieved it, so the electrochemical detection of molybdenum goes perfectly well. We see the typical peak of molybdenum located on the position which is the same as in literature, and we went further. We add the additional pesticide, so this particular result was obtained in the pesticide mixture. Molybdenum was mixed with the imidacloprid, and we also see the peak of imidacloprid reduction, but in the different regions. So at the moment we could achieve the electrochemical sensor on the graphene polymer composite and the SERS detection on the silver polymer composite. So and the further idea is to make the conventional actually SP sensor by direct laser writing, but it would be two-step laser writing. So we would make the working electrode and the counter electrode out of the graphene polymer composite and the reference electrode out of silver polymer composite, and we would be able to achieve the electrochemical sensing on the working electrode and subsequently the SERS sensing on the reference electrode. So here is the conclusion, and I would like to thank my team in Tomsk Polytechnic University, especially our supervisors. One of them is here, is Evgeny Sherebet, and Raul Rodriguez. This work is supported by the joint project of Arabia and DFG. I would be glad to answer all of your questions.
Thank you, Maxim, and let's think. And now we have time for questions. Please, who wants to ask? Yes, Dmitry.
Yes, thank you. If I may, very interesting results.
Could you please?
Yes, very interesting results, but I must have missed the point here about the physical processes of the laser deposition. I'm sorry, I forgot the term that you used. Laser appropriation of the nanoparticles into the matrix. What is the physical process there, physical mechanism?
The physical process is the nanoparticle absorb light. So the light transduces into heat, and the polymer, which is the substrate, got heated. So first, then the melting temperature of polymer is reached, the polymer got melted, and the particles start go into the polymer matrix, to this melted polymer. But if the radiation still continues, the temperature continue to rise. So you're gonna have carbonization, then the temperature gonna reach the pyrolysis.
So, as far as I understand,
physically it's a photothermal transduction.
Photothermal transaction, I feel like it's a diffusion process, diffusion of the nanoparticles into the substrate. So here's the question: wouldn't it affect the resulting conductivity if you have the not the nanoparticles, I don't know, clusters or structures made of the nanoparticles, but the nanoparticles dispersed in the polymer matrix?
So we actually didn't study the conductivity so well, but just the quick measurement showed that they are highly conductive. I mean, the structures and the lines about 1 centimeter show the 0.5 ohm resistance. So they are highly conductive. There is no interruptions. They are conductive all over the surface. Because what you see in SEM, that's the top. That's actually the particles which are melted on the welded on the ones which are in the polymer. So you also have the conductive network inside the polymer.
Correct, thank you.
Any questions?
I have question.
Yeah, yes, please.
And I also have, I would like to notice that you showed the picture and told that the particles were welded, but what it is seen on a picture is not welded but sintered. I think it's more precise.
Yeah.
For calling that.
The term, I could say in Russian that it's spikание.
Yes.
Maybe the translation is
the English for spikание is sintered. So, and the question is, have you used DFT modeling for your Raman spectra interpretation?
No.
So
we're actually planning to do it.
It's a very good technique to know what is exactly occur in your Raman spectra, and to support your experimental findings is to use the DFT modeling for these Raman spectra. And the small question is, who is the eldest of your participant of your group?
Eldest.
The youngest, oh, I'm sorry.
Youngest, it's the child of our bosses.
Yeah.
Yeah.
What is he doing? Okay, sorry, that's just a joke.
Yeah, thank you.
Thank you. It's good collaboration with children. Yeah. Any question? Yeah. No, I have one question for Maxim, and my question is related to modification of your layer, your graphene layer with different organic molecules like aniline and sulfaniline and so on. Can you please switch on this slide? Yes, it's just maybe. I know.
This one, yeah?
No.
The modification?
Modification, it's maybe 7 or 8, 6 or 7 with organic. Yeah. This one, 7. Yeah. Yeah, I know that gold layer very easily connect and make bond with sulfur group. But in your case, which layer?
It was silver.
It was silver. Yeah. Ah.
So
Okay.
Silver has pretty much the same affinity to sulfur as gold.
Okay, and can you recognize the bond of silver and sulfur?
Actually, that's a tricky point because the silver-sulfur bonds, the pure silver sulfide bonds are laying in this region, so in the region of here, and it would be hard to distinguish which are coming from the pesticides or which are coming from the natural sulfidizing. Okay. And these bonds are not like very intensive.
Yeah. Thank you very much. And if there are no questions, let's thank speaker again. And I want to say that our section is closing now. I want to say thank for all participants for hot discussion, for many questions, and now we have time for dinner and session laser meta interaction 2.2 will start from 2:20. Yeah. See you in same room and 2:20. Thank you very much.
Здравствуйте, уважаемые коллеги. Будем начинать нашу сессию. Laser Matter Interactions. And so we have two changes in our program. So first, Sergei Arakelian has cancelled his presentation. And last presentation of this section by Vladimir Mazhukin is transferred to poster format and will be presented tomorrow during the poster section at 16:20. So then our first talk will be given by Maxim Khomenko, an insight into property process parameters, correlation of laser additive manufacturing, thick precipitates. So please.
Hello. Can I use this? Okay. So, I would like to present my work on laser additive manufacturing, and I will tell how numerical simulation can give an insight into the process parameters correlation in this process, exactly in manufactured metal matrix composites. First, it would be a small introduction. After that, I will tell about the model and its reliability. After that, I will talk about homogeneous materials, and at last about the metal matrix composites. So I'm talking about the additive manufacturing, where the computer-aided design is used for layer by layer part production. Especially I'm using the laser metal deposition, where a powder and the laser are using the jet transferred to the substrate to make a layer, and in this way we can make some complex part. So how can numerical simulation and numerical modeling help to investigate laser metal deposition? So it can support experimental results, showing with another way the same results that are gained experimentally. It also can reduce experimental work, and it could show an insight to a complex phenomena that occur in the laser metal deposition. So here I would like to show how numerical simulation goes now. We've got some experimental laser center with whom we've in contact. We discuss the task being in a computer center, and we finally give some recommendations on optimal processing parameters to the experimentators. It could be more automated if we have some web interface to make a task for simulation, which will be transferred to the computer center, and a processing map could be could be developed due to the numerical simulations. And the next step could be not only some optimal parameters gained from the simulation, but the whole building strategy of the part production could be gained from numerical simulation. Surely with some iterations with the experimental part. So we use high-performance computing for our simulations. We've got such a facility in our place, which is almost enough for our tasks. So we use open CFD software for numerical simulations of the heat transfer in the melt pool. We also use an open source molecular dynamics software for computational chemistry. And we also use a Gaussian 16 for Raman spectra interpretation. So these are the segments of our model. I won't present here the equations. The interested reader could look inside the papers, published papers. So the segments include almost all phenomena which occur at laser cladding, at laser metal deposition. So our microstructure model was also calibrated on some experiments and was used for another experiments with different parameters and showed rather good results. These are the development of the validation of the model. So we first had a thermal model which we validated only on some track parameters, single track parameters, and in not very wide in a single processing parameters. After that, we developed the model, and now our last paper has the model was validated for a wide range of the track parameters, for the wide range of the processing parameters, and also include the microstructure validation. These are the results of the validation of the model. We've got rather good correspondence to the experimental data for the width, for the height of the track, and for the average size of the homogeneous material. But we've got not very good correspondence in the for the penetration depth here, but this was not a very big problem, because in a single track or in a layered geometry, the penetration depth plays not high role for homogeneous materials. So what we have for the processing parameters influence, the dependencies are rather straightforward. They are published in many publications. So we've got the same for in our simulations. So the scanning speed increase results in average size of the microstructure. And the width of the track decrease, And the laser power have the opposite influence on the same track parameters. But as I say, it's rather straightforward, and that was not the aim of our investigation, because we use laser metal deposition for additive manufacturing, which is the multi-layer technique, and the objectives are to build a 3D part with some certain quality and properties. So if you have some objectives, you have to first optimize the single track laser cladding, laser metal deposition. After that, you have to find the optimal single layer processing parameters using hedge spacing and some idle time or so. And after that, you have to find the optimal properties for the multi-layered structure. After that, if you have any other objectives, any other part or any other needed microstructure, you have to change processing parameters, which will result in the track parameters change. That's why you have to repeat your steps, the single layer optimization and multi-layer optimization to get another objectives. So, and the idea that we propose is to have only one step, so to optimize single track parameters to get the track with the same geometry, but for example with another microstructure. That's why we can exclude the next two steps in our optimization. So we've got two processing parameters which influence in opposite directions, so we can adopt these parameters to get this idea realized, which was done in modeling. We've got tracks with similar height and width, and have different average microstructure in it. We also realized this in experiments, which we show that we can do it in a real situation. This is published in the Journal of Manufacturing Processes. After that, we go to the single layer microstructure. We also realized this for a single layer simulation, and which would be soon published. Yes, that was about the homogeneous materials, but also we use our model to get insight into the metal matrix composites fabrication via laser metal deposition. We added, we considered some situations such as heterogeneous precipitation on unmelted carbides, which is a rather common situation for the metal matrix composites. We added some equations to our model to account for this precipitation. We can calculate the average size of the precipitates. We've got, for now, not very good comparison for the macro parameters of the track, but still we've got the same design for the thin wall, which could be seen that it's the same for the experimental thin wall. We see that the precipitates are localized in the top of the thin wall. It's the same for the experimental thin wall, but also it got some precipitates localized on the border of the thin wall, which we can't see in the model. But still we've got some coincidence with the experiments. So after that we also considered another geometry. It's a box sample, a full box for a titanium aluminate with titanium carbide reinforcement. We discuss here the situation where there is no unmelted carbides, and all carbides are precipitated from the very small values, so homogeneously. We've got a published paper with a lot of data on this experimental situation, but still without the contact with the experimentators, you can't make simulations because some parameters are absent. So we've contacted with these experimentators, and with them we developed the model. There were some experimental hypotheses in experimental paper, which is shown here. So they told that the precipitate radius is decreased with the layer number, and they think that it is connected with the sequential reheating. So the next layer comes, and it remelts the previous layer, and the coarsening of the precipitates occur in the lower layers. We also see that reheating increase the precipitates radius in the model, but due to the lack of the penetration, the maximum is not on the lowest layers, but in the middle. But nevertheless, it is higher than on the top of the box sample. So, in conclusions, I can tell that a robust model for microstructure investigation in laser additive manufacturing was developed. The method for changing the average crystalline size while closely preserving the growth parameters is shown. We show that the microstructure could be controlled in multi-track laser cladding preserved layer geometry. That's why we can exclude steps of optimization of layer geometry and scanning strategy. And also two typical situations we can see that for metal matrix composites fabrication via laser metal deposition and a multi-layer sample and a thin wall, but some further development is required for the support of the experimental findings. Thank you. That is all. Any questions?
Thank you very much. Let's thank the speaker for nice presentation. And please, this talk is open for discussions now. Are there any questions? I was a bit curious if the software that you applied for your simulations covers completely all your requirements, or does it have any limitations? Did you have to provide some description of some mechanisms of your phenomena into the model, or it's already included, everything?
The most part of the model is realized in open form software, and it covers all the phenomena for the model, but we also use some scripting for numerous simulations, some Python scripts, and so for only for data analysis and numerous simulations. So
no, this is clear. I mean that, for example, one of the most crucial parameter in your results is grain boundary energies. Are they reproduced?
Sorry, what?
Grain boundaries. So you have a lot of grains, right?
Yes.
So they have energy, yeah? Grain boundaries, stacking folds,
Yes.
dislocations. If the energy of those dislocations or grain boundaries are reproduced in your simulations, do you have any comparison with experimental data?
You see, the both model are some describe the microstructure, but not model exact grains of the precipitates or the grains of the homogeneous material. So we use modeling to describe some parameters such as average size of the grain, but we do not model the exact grain. So we've got a model.
Okay,
of the
but for example, the resulting structure, can it be somehow characterized both theoretically and experimentally? I mean, for example, stress tensor, if it can be extracted from simulations, and bulk modulus, if it can be compared with experimental value of this steel?
We've got some development in the properties of the resulting layer, so we can calculate the hardness of the layer using the average size, the average grain size, but this is still in development, so it's left for the future.
Yeah, that would be interesting to have the comparison of the experimental measurements as well.
We are still comparing the macrostructure, so we can do it using the BSD and so.
Yeah, thank you very much. So, are there more questions, please?
I have one question, and I didn't see some description about laser parameters.
Laser parameters?
Yeah, which type of the laser?
We use some common processing parameters. I would call it high speed laser metal deposition. So the speeds are something like tens millimeters per second, and the other parameters are
adopted to get these. You can apply for this paper where we show everything. So, which parameters would you like to discuss?
Laser power is a pulse regime, and another one.
Laser power is it's dependent on the situation. So for in Cornell we've got something like 1 kilowatt laser CV.
1 kilowatt.
Or so.
Okay.
Okay, then let's thank the speaker again. And we go to our next talk, which will be given by Alexander Dubrov. Porosity reduction and structural features of 316L stainless steel fabricated using combined laser metal deposition with laser remelting. So please.
Hello everyone, my name is Alexander Dubrov. I'm from the Institute on Laser and Information Technology, which is branch of the FSRC Crystallography and Photonics, Shatura, Moscow region. And my talk is going to be about porosity reduction and structural features of 316 stainless steel fabricated using combined laser metal deposition with laser remelting. So, sorry. So the laser metal deposition is perspective technology which have several advances over the traditional manufacturing technology, and it can build the parts of complex structures from powder, from metal powder and some other materials, and the key idea is to bring the laser and the powder material to some local area, so the laser can melt the substrate or previously deposited material. The powder gets into the melt pool, melts, and after it solidify, after the mutual movement of laser and substrate, we get a bead. So repeating this step over and over, we can make the desired 3D part. And for some years there are a lot of interest in the science community to these technologies, but still there is some problems here, and one of it is keeping the parameters so they are optimal in all the points of the building path, and this mainly true for the complex part like this one, which consists of solid full-bodied parts and thin-walled or overhang parts, so the thermal conduction features over the building path are different. So in the situation when so mainly we need to keep the thermodynamical parameters optimal to get desired quality of material. If we fail to do so, problems like porosity, or cracks, or unmelted regions can bring up. So here two, by the way, types of porosity which mainly can be faced in LMD. It's intralayer porosity or gas porosity, which basically is gas bubbles from the melt, which did not have time to escape, and after solidification we have this. They round in shape and 10 or less microns in size. Or another type is interlayer or technological porosity, which bring if we fail to keep the optimal parameters and bring lesser than needed energy to the process, so we do not melt all the material and get unmelted regions. So one of the approaches to deal with these problems is to have a bad quality when we fail to match the process parameters, is to modify the original laser metal deposition technology to combine it with another technology of laser remelting. As laser remelting is a well-known technology and it's used for surface modification, but in this combined technology it's used after each layer is built, so all good it can bring to the one layer of reducing the porosity and changing the microstructure the way we like, so making it for each layer of multi-layered part can make the inner part, inner material of the part better. So we perform the experimental investigation of such combined technology, and for using the stainless steel 316 and using the LMD based technology, which we thought should bring some of technological porosity. So we varied the scanning speed and the bed overlap, and for each of these 9 base technology, for each of them we varied the laser remelting scanning speed, which was set at proportional to the base speed, from the 60% to 600%. And after that, the samples was investigated for residual porosity. The porosity was measured separately as technological and gas porosity, and also we measured the mean hardness and the mean cell spacing. Okay, so here the comparison of the LMD only regime and the best of the combined regime for this particular LMD regime. So for LMD we have the technological porosity from 0.5% to approximately 1.4%, and after the remelting we always had the opportunity to reduce the porosity 1.3 times to almost 7 times less than the initial porosity. And here all the data obtained concerning the interlayer porosity, and they given in bands. So for each band, the base LMD technology is the same, and the points in bands are ordered in ascending of remelting velocity, and the colored point is LMD porosity. So mainly any combined regime reduced the porosity, and the most pronounced reducing when we use remelting velocity equals or less than deposition velocity, and in that time we reduce to 2 and more times. And still, when we use remelting velocities 2 to 6 times faster than deposition, we're still reducing the porosity, but from 40 to 70%. And to analyze the mechanism behind this, we can take a look to the penetration depth. Here's the green points. It's a penetration below the wall layer. So the X is inverted. So if we have a point on the 0 line or below it, then we remelt all the layer, and sometimes we went deeper. And as expected, the more pronounced, the deeper we remelt, the more pronounced the reduction of porosity. But still, even we do not remelt all the layer, even we remelt only part of it, we still reduce the technological porosity. And here, what we think, which mechanisms are behind this. So if we remelt all the layer, so we bring the energy to the unmelted, bring the energy again to the unmelted part, the unmelted region, bring the gas phase to the melt, to the bubble, and with use of convection, evacuate it through the top. If we do not remelt all the layer, but still we overlap partially by the melt pool the pore, the leaking of the melt could be, so partially gas transferred to the melt and evacuated, but we probably could not get the good contact between new material and the bottom or walls of the pore. And if we have even less deep melt pool, so we did not overlap the pore, we still, as we saw, we still reduce the porosity, but now the effect of the remelting is in smoothing of the surface. So by smoothing the surface, we reduce preconditions for porosity generation of the next layer. Okay, for gas porosity, it all was for technological porosity. For gas porosity, the things are a little different. The level of gas porosity is low from the beginning, so the red, yellow, orange dot. And for it is LMD. After single LMD, we have gas porosity is around several hundredth of percent, and with some regimes, combined regimes, we can make the gas porosity even less, but in most situations we make it worse, and the faster the remelting speed, the more gas porosity we have, and up to 2.5% and in very low velocities, when we use low deposition velocity and low coefficient, we also growing the gas porosity. But in absolute values are not so bad, and choosing of regime is a question of compromise, because we can get several hundreds of gas porosity, of extra gas porosity, but reduce several tenths of technological porosity. And here we see, like on the original LMD we have technological porosity, and after the remelting technological porosity are gone, but we bring new gas porosity. And the interesting thing is, if we get all these dependencies to one x, to one coordinate of velocity. Here we have not coefficient, but velocity. Yeah, we can see that there is some optimal regime of remelting concerning the gas porosity, and it from around 7 to 11 millimeters per second. And if we go beyond this regime, we make more gas porosity, and this because of convection inducing extra convection movements and in a melt pool, so we capturing the gas from the atmosphere. So if we go too slow, we overheat the melt pool, and if we go too fast, we probably make too high surface gradients, surface temperature gradients. And another interesting effect of this combined technology is layered structures. So if the penetration depths of the first stage of the deposition and the remelting stage are different, in the final material we have regions which was solidified last time by the deposition, or the different regions which was solidified in the remelting region. And the properties of material of such regions can be different, because different thermodynamical conditions in there. Here we see that the cell spacing in a remelted part is different, and for different combination of parameters, we could have any ratio, any proportion of the volumes of material solidified when deposition on the first stage, or material solidified on the second stage. But the remelting velocity is the main factor which affects the thermodynamical condition. So the higher the remelting velocity, the faster the cooling rate, the more the temperature gradient, the finer the microstructure, and more further the microstructure of remelted part from the deposited part. But the more the faster the remelting speed, the thinner the layer. So for the integral properties of the material, the dependency is complex because we have two concurrent mechanisms. So here the hardness and cell spacing dependencies, and they both integral. So we see very complex behavior of the complex dependencies of them on the remelting velocity, and only we can say that hardness goes lower when we remelt very low with very low speed, and that cell spacing after remelting is less than in the original LMD part, and the other dependencies are rather complex. So if you forgive me, I would not repeat all the conclusions, and thank you for hearing me, and if you have any question, I'm ready to answer.
Thank you. Let's thank the speaker. So please, this talk is open for discussions now. Can you tell me, please, how large are the metal powder grains that you deposit on the
size of the powder?
Yes.
It's from 40 to 100 microns.
Ah, it's a microns. Okay. Would you think your experimental setup work for nanometers?
Can you bring the microphone a little closer?
Yeah. Would you think that your experimental setup can operate with nanoparticles like 30 to 50 nanometers size?
Particles, grain size less than 10 microns, maybe less, is not good for this technology, because we bring the powder with gas stream, so very fine powder will go everywhere, and it's hard to bring it to the place with this technology.
Okay, so what is the bottom limit of the grain size that you would consider for your technology?
I cannot answer to the question. We mainly work with several tenths to 100 microns.
Okay,
maybe
thank you.
200.
Are there more questions, please?
And after some very interesting results about the porosity, and my main question is which regime is best? Which regime without some porosity, in gas porous or industrial porous, and another one? It's possible to synthesize this big part without pores?
Are you asking which regime is the best?
Yeah.
You know, this research was not intended to select one regime. It was intended to see which mechanisms can emerge in this combined technology. So we just showing you all the polarity of such effects we see. So I think the best regime is depend on purpose. If we need if some amount of porosity is accepted, then we can use faster remelting. With faster remelting, we did not spend more time, we did not spend more energy, and we reduce the vast amount of the porosity. So it's like high throughput production. But if we need, if any porosity is not allowed, so we need to set the second stage to a rather low speed, the same velocity as was in deposition regime or less, and use it.
Okay, thank you.
Thank you. Let's thank the speaker again.
And our last speaker of this session is Dr. Ivanov from, how is this? Excuse me, I need some. Ivanov from Liberty Physical Institute, and he will speak about modeling of laser-induced surface structures generation due to the surface plasma polariton excitation.
Yeah, thank you very much. Before I start showing the results on non-structuring of surfaces assisted with excitation of surface plasma polariton, I will speak about general concepts of our approach and the structures that we are interested in general. So these are examples of nanostructuring of material surfaces. Mainly we are interested in the surface functionalization that can make them hydrophobic, for example. Nanostructuring can be also utilized in waveguiding, micro-optics, biosensing applications, diffractive writing. And in particular, in this presentation, we will consider the structures due to a single pulse, single structures due to a single pulse. It can be also kind of nanobarrier structures obtained in laser centrum Hanover, periodic structures, and finally we go to so-called laser-induced periodic surface structures, SLIP structures that understood as generated due to excitation of the surface plasma polariton. And these are examples of such structures obtained in GUO Chinese Photonics Laboratory in Changchun. And these experiments garnered in this laboratory resulted in generation of 1D, 2D, and 3D structures in the multi-pulse regime. And our main purpose, therefore, is to study the mechanism responsible for generation of such structures in order to obtain the resulting material surfaces with pre-designed properties. The properties that we are interested in can be morphological properties, optical properties, magnetic properties, and so on. So we want to generate surfaces with demanded properties. So in order to study the mechanism of formation of these structures, we choose the molecular dynamics because on one hand, it benefits over continuum modeling because in the continuum modeling, under conditions realized with ultra-short laser pulse interactions with materials, the temperature and pressure gradients and the nucleus of new phase that shrinks down to just several interatomic distances hampers the applicability of continuum modeling, and therefore molecular dynamics simulations, especially in super large scale modeling, make it possible for a direct comparison of the modeling results with experimental measurements, and still with atomic precision can reveal the kinetics of non-equilibrium phase transitions induced with ultra-short laser pulse. On the other hand, the molecular dynamics much more efficient as compared to ab initio calculations where one solves Schrödinger equation, but there is an important and very essential step which is discarding. We completely discard information about electronic structure here. So And this allows us to make a step from quantum mechanical representation to classical representation of atomistic motion governed via second law of Newton, where interatomic force is defined as a gradient of interatomic potential, which is a semi-empirical function parameterized to reproduce the material properties at normal conditions. And the applicability of this method, molecular dynamics method, is based on the comparison of the de Broglie wavelength with the characteristic interatomic distances, which holds true for most of the materials, except the lightest materials and those that expose strong polarity of molecules, for example, water molecules. So in most of the cases, such approximation, classical approximation is possible, and therefore with atomic precision we can study, for example, nanosecond laser melting of silicon and so on. But for metals, the classical molecular dynamic representation, especially when it comes to femto and picosecond laser pulse interactions, is not possible because we discarded completely information about free carriers electrons. But in femto and picosecond laser pulse interactions, free carriers, the effect of free carriers becomes dominant because it's due to free carriers that we have laser light absorption by metallic target. We have fast electron heat conduction, and we have strong electron phonon non-equilibrium developed with ultra-short laser pulse. So if the pulse shorter than characteristic electron phonon relaxation time, which is on the order of 10 to 50 picosecond, then the presence of free carriers is a dominant, and it governs the evolution of the irradiated target. So despite the fact that we discarded the information about free carriers, we now somehow must account for the presence, and we should account for the effect of free carriers in the molecular dynamics via additional model, which is called two-temperature model, which is a system of two differential diffusion equations standing for balancing the energy between electrons and phonons. And this model can describe fast electron heat conduction, electron phonon non-equilibrium, and the absorption process by conduction band electrons. But as I mentioned before, in continuum, this model applied alone is not a good idea to describe fast non-equilibrium phase transitions, which can be done with molecular dynamics with atomic precision. So in the combined method that we used in most of our models, we merge the advantages of these two approaches within the scale of a single computational approach, where the electronic system described in continuum and kinetics of non-equilibrium phase transitions described with atomic precision with molecular dynamic approach. Thus, we can start already studying investigation of the mechanism of nanostructuring process. For example, structures produced at laser centrifugal depending on the pulse shaping, spatial modification can be done in different geometry. And for that purpose, the combined atomistic continuum model was done in a parallel version so that the results of the modeling can be directly compared with the experimental observations. So in order to cover the experimental scale, we choose only a central part of the modeling feature simulated with the combined method. We divide the whole volume to number of cells. Each cell is governed by a separate processor, and inside of each processor, in three-dimensional mesh, we solve simultaneously continuum description of free carriers and atomic motion with molecular dynamic approach. So this model is capable of describing nanostructuring process at the experimental scale, and this is animation from this simulation. So you can see the atoms here colored by the potential energy. You can identify solid, liquid in the central part, surface, generation of dislocation planes due to rapid expansion of the central part of the film, and solidification process as well. The mechanism of the formation of these nanostructures was identified due to interplay of two competing processes. This is the relaxation of the laser-induced stresses responsible for the growing feature the idea is that we heat the material with a laser pulse faster than this material can relax in response to that heating by means of thermal expansion. So we have accumulation of strong compressive stresses, relaxation of which proceeds via recoil pressure waves, you can see, and due to propagation of the strongest compressive wave, we have acceleration of the molten part of the material in the, how to close this, okay, in the central part of the material, and this acceleration results in establishment of hydrodynamic motion of the molten part of the material, and the nanofeature grows. And on the other hand, solidification, fast solidification of this nanostructure proceeds via three-dimensional electron conduction process. So in three-dimensional case, the electrons, due to presence of strong temperature gradient, the temperature of these electrons goes even below the lattice temperature, and now the electrons act efficiently as a freezer for growing feature, which causes its fast resolidification. So similar simulations, similar modeling was done in order to study the periodic nanostructuring that was obtained in laser laboratorium Göttingen due to mass projection setup by means of interfering two beams. They achieved in redistribution of the laser intensity across the surface and periodic structuring of the surface of material within the 40 microns laser spot on the material surface. So the result of modeling were directly compared with the experimental measurements and was quite successful. So now we must think about the leaf structures, formation mechanism, and how to achieve the generation of surfaces with predesigned properties. So in order to account for the plasmonic effect, so let's first consider the general concepts. So this structure were obtained in multi-pulse regime, but leap structure was also detected in a single pulse regime by Gurevich laboratory. And general concepts is that, okay, we have incident electromagnetic wave, and if we have a local jump in electronic density, which can be seen as a defect or, for example, a step on the material surface. So here we have a local jump in electronic density, and this local jump can be, and due to this local jump, the collective motion of electrons in this place can be excited with the incident electromagnetic wave that will interfere with this incident electromagnetic wave, resulting in the resulting interference will be in spatially modulated heating of the sample, spatially modulated temperature, electronic temperature distribution, and heating of the sample in correspondence. So as a way to introduce the surface plasmon polyaryton excitation, we suggest to include this mechanism into the source term of the two-temperature part of the combined model. So normally this source term can be represented as a Gaussian pulse. So we have reflection process, Lambert-Spears law, attenuation of the electromagnetic wave, and normal Gaussian in time. In the case of, and of course this approach does not include any information about the electromagnetic field, incident electromagnetic field. So as a first approach, our colleague from Pavel Terehkin from Technical University Kaiserslautern suggested to define this heating source as a divergence of the Poynting vector, which is a cross product of electric and magnetic fields. And now all these components are included into consideration, and the corresponding source term can be extracted. Of course, it's much more complicated. It considers of several components. Okay, and as an example, so this is the source term as a function of depth and lateral distance from the center, and this source term accounts for the excitation of surface plasmon polyaryton. And it's also a function of wavelength. So for 400 nanometers, it decays faster. So now we want to test our source term in the combined atomistic continuum model. So this is a side view. It's an electronic temperature field which accounts for the surface plasma-opal electronic excitation and for normal plane waves. So you can see as the 200 femtosecond laser pulse propagates with time, we have now modulated heating of the electronic system as compared to just a plain wave absorption in the case of when we do not account for surface plasma-opal electron. So now we want to apply our complete model, which atomistic continuum, and which includes surface plasma-opal electronic excitation via the source term, and compare our results of modeling with experimental measurements. So for the experiment, a scratch was produced on the gold film, and the laser pulse was focused on the edge of this target. So the results of modeling, our first approach, the scratch is assumed at the center. Here's a molecular dynamic atomistic picture. So atoms here colored via central symmetry parameter for local identification between solids, defects, liquid, surface, and vapor. So here, initiation of melting, and on the surface, red particles, it's initiation of vaporization. Here, we will show temperature field of lattice. So you can see that shortly after laser pulse absorption, we have modulation of heating, modulated heating of the material surface, and then formation of structures. But the incident influence in this case was a little bit higher than the ablation threshold, unfortunately, and all our structure got destroyed. Also here we can identify the formation of dislocation planes due to rapid expansion of the heated layer, formation of internal voids and so on, again due to relaxation of the laser-induced stresses, because again here we work under conditions of internal stress confinement. So our first approach was unsuccessful, but then we decreased the incident influence. Here is a mistake, here should be millijoule per centimeter square. And now you can see that, so the edge is assumed here. Now you can see that relaxation of laser-induced stresses results in gradual formation of structures, and then process of resolidifications takes over, and finally we have our ellipse structures simulated and directly compared with experiments. So let's see on the results of experimental measurements. As you can see, the ellipse were formed directly after the edge with exactly the same decay as it was simulated, and the period of this ellipse structures coincided with theoretical predictions, of course, and they always parallel to the edge. For example, here there's additional scratch was done, and those ellipses again got in the parallel directions here. So, to conclude, the effect of surface plasma-opal electronic excitation was accounted in our combined atomistic continuum model, which allowed us to reproduce the experimental conditions, allowed us to reproduce the formation of ellipse, and now we basically have a powerful numerical instrument in order to design the experimental conditions for generation of surfaces with pre-designed properties. So thank you very much for your attention.
Okay, thank you. And open discussion, please. Any question?
So thank you very much for very interesting presentation. It is very surprising to see such a model, two temperature model. So could you please tell some more about this model? For example, where have you taken the numbers? So the parameters for the model. And also, where can I see that the period is the same in modeling and in experiments? I couldn't get it.
So the basis of this combined method described in this article yet, and then number of modifications, you can have this citation here, and this here, and a lot more actually for the latest simulations.
No, excuse me. The question was, I don't need the numbers. I just want to know, is it a problem for such a model, for two temperature model, to get numbers, the parameters, which could be referred.
Okay, I understood you. Okay, so basically the two-temperature model, each of the parameter entering two-temperature model can be considered as a separate model, separate phenomenon. So all these parameters are subject to investigate experimentally and theoretically and published in a number of papers, so you can find them easily. For a number of materials, specifically for metals, of course, and they can be taken as constant as a first approach. In our case, we took the most updated, realistic description of all these parameters. They are a function of not only electronic temperature, but also lattice temperature, densities, accounting for density of states of the material under conditions of irradiated target in our numerical experiment. Yeah, so the description of each of the parameter is a complex, separate model. But you can find the information in our publications, for example, for sure.
Thank you. And for the second question, so you've told that the period is the same for the model and for the experiments. I couldn't get it.
The excitation of surface plasma-polar electron, the physics of this excitation, was placed in the source store.
Yes,
Yeah, so based on the parameters of the incident electromagnetic wave, this source store can be basically decomposed to three inputs: laser-laser interaction, laser SPP, SPP-SPP interactions. So this source now includes reflection, attenuation. It also accounts for polarization, and it accounts for the wavelength. And this source results in the intensity, laser intensity absorption redistribution across the surface. So all the information about SPP, surface plasma-polar electron, is now placed to this heating source, which is participating in our combined model in the continuum part of this model, responsible for the description of free carriers.
Okay. And the question is, how can I compare the results of your model with experiments?
Okay, for example, here, for example, this one. So you have the scale here, right? You have, you can calculate the distance between the peaks, and you can compare them with experimental measurements.
Have you done that?
Yes, yes. It's published somewhere here,
Okay.
I guess, yes.
Okay. Okay, thank you. And the fluence was the same, so all parameters?
There was one problem actually, because the fluence, the threshold for leap structures generation detected in experiments was something like 160. We still cannot identify the reason of this little discrepancy. We're still working on that.
Okay, thank you.
May I ask, first, thanks Dmitry for very clear presented talk. Not so easy, but clear. My question is, this explanation is done for evaporative mechanism, melting evaporation mechanism of appearance.
Vadim, I cannot hear, sorry.
Okay. For my understanding, this mechanism is applied quite correctly for evaporative mechanism of leaps appearing. But there are many other types of the leaps. For example, it's possible to think about the thermochemically driven model of leaps. This is my question.
Yeah, I understood question. I know that there are still debates, a lot of debates about different mechanisms. There are different types of leaps, of course, I know. But to my feeling, it all comes to a relaxation of stresses. It looks for me like, if you have a plate with a sand, you now start shaking it. the surface of resulting sand surface, it somehow reflects the waves that you apply with the shaking. Yeah? So it sounds like what we have observed in the experiments. So the way of introduction of surface chemistry, of course, is not realized in our model. So we cannot model any chemistry because we have absent, the electrons are not explicitly presented in our model. Currently we're working on development of models that include DFT simulations as well. So from DFT you can extract the rules of chemical reactions, rules of surface chemistry, and you can put it into the combined model as a separate add-on. That's the way.
Okay, thanks a lot.
Okay, dear colleagues, any question again? No? Okay, it means that our session is closed and we have some time for coffee break and discussion. Thank you all participants for a very interesting discussion and presentation.
Yes. Okay. Dear colleagues, the time is over. We should start the next session, the last session of laser-matter interaction of our conference. Unfortunately, I cannot see my co-chairman and first author, Dr. Antipov. In this case, first will be my presentation. It's titled femtosecond laser plasma driven nanoparticle formation in aurum aqueous solution. Dear colleagues, today I would like to present for your attention the work performed in the General Physics Institute in Moscow, Russia. The title is already sounded. You can see it here. Also, you can see the list of my contributors, my colleagues, which participate in this work. So this work is devoted to the certainly interaction of intensive laser light with matter, particularly with liquids, and the specific task in which we try solve was production of metal nanoparticle in the liquids. Particularly in the water. So here you can see the basic mechanism, which now is considered to be well known. As opposed to traditional approach, which is ablation of solid target, this approach based on the photoreduction of metal salts in the water. And all you need to do is produce plasma in the solution of metal salts. So via nonlinear absorption, you produce so-called wet electron. These electrons differ very well from the usual free electron which we produce in the gas medium or quasi-free electron which we produce in the solids. These electrons interact very strongly with the parent ions and moreover, when time progresses starting from the excitation, the neighboring water molecules create something like cage, and electron gets trapped in this potential well, and this is state which is localized even more than wet electron. This electron usually is referred as solvated. But in any state, wet electron and solvated electron principally can meet the positive ions, metal ions, reduct them and produce neutral metal atoms, which in turn can meet each other and coalesce, producing nanoparticles. So everything is okay, but there is a basic problem. We don't know condition of initiation of this photoreduction, photochemistry. One model says that the optical breakdown is the key feature, another says the supercontinuum emission is the most important thing, maybe something else. So in this work we try to solve two tasks. First one, to study the optical properties of laser-induced plasma in water and its dynamic. And second, to study the effect of plasma on the course of photochemical reaction in water solution. Here you can see outline that I will follow during my presentation. I will shortly say about experimental setup that we used. Then I said about two regime, low energy regime and high energy regime of plasma creation. Then I try to find and point out the correlation between plasma properties and nanoparticles generation in water, and I will make some conclusions. So this is experimental setup that we used. This setup enabled us to measure absorbance and refractive index of plasma that we create. So we used titanium sapphire laser. The pulse duration was typical, about 100 femtosecond. We use fundamental harmonic. As usual, when you study dynamics of fast processes, we applied the pump probe scheme. It means that we divide the radiation into two parts. First part, the pump part, was used to irradiate the water cell and create the plasma. Second one, probe part, passed through the delay line, then through the water cell and plasma, then through the imaging system and interferometer, and create interferometric pattern on the screen of CCD camera. Analyzing this interferometric pattern, we can extract the absorbance, as I said previously, and refractive index change in the plasma which we produced. Here you can see the examples of such interferometric pattern. All these examples were made in the low energy regime. It means the energy of the plasma, energy of the laser radiation was in the range of sub-microjoules, or achieved few microjoules. When the laser energy is about half microjoule, no plasma was detected in our condition. We only see the propagation of cloud through the medium, through the water. This is a result of Kerr effect, so this is manifestation of nonlinearity properties of water. And of course, this cloud coincides in the time and in the space with the light wave packet. When we increase the energy up to about 1 microjoule, the picture becomes much more complicated. Here you can see the pulse propagated from the left side to the right side. First of all, on the front of pulse, Kerr effect. Then you can see refractive index dip, which is attributed to the appearance of wet electron. Then we found on the tail of pulse, unexpectedly we found the enough abrupt surge of refractive index. Now we attribute this effect to the Kerr effect in the plasma, not in the water, but in the excited water, and it's strongly much higher than Kerr effect in the water. When the pulse left the laser waste, you can see the narrow channel consisted from the wet electrons, which evaluated and solvated during about 2 picoseconds. As a result, the refractive index of irradiated zone increased up to some maximum. Then during 200-300 picoseconds, the recombination takes place, and as a result, the index fall up to 0 almost. And finally, the final stage at the nanosecond time, the refractive index increased again. We think that this is a result of heating of water, and this refractive index is proportional to the temperature and pressure into the irradiated zone. So this plot demonstrates all the dynamics that I described. Once again, this maximum is due to Kerr effect. This is appearance of wet electron. Then we see Kerr effect on the plasma, solvatation process, recombination, and precavitation. I would like to emphasize that here at solvatation regime and recombination, the refractive index is proportional to the number of carriers. But here in precavitation stage, it's proportional to the temperature and pressure of water. So we measured the refractive index and absorbance of water, excited water, after 2 picoseconds after excitation in the maximum of refractive index which produced by the solvatation. You can see these dependencies on the pulse energy. Both follow the power law with exponential factor about 5. So we have deal with the multi-photon absorption, and 5 photon is in good correlation, 5 photon absorption is in good correlation with the known value of ionization potential of water, which is 6.5 eV about. Also from the absorbance, we evaluate the number of carriers that we produced in the saturation regime here. And we found that this value about 10 in 19 carriers per cubic centimeter. It's not very high value, because if you try to estimate the energy which some number of carriers can store and then return to the water, you can find this in energy can provide only 3 degrees increase in temperature. So it's no very high heating. But I remember that, I remind that we work in the cavitation regime. Under our excitation, under our irradiation, we produce some microbulb in the water. And for this, you need at least 100, 200 degrees centigrade increase in temperature. What the origin of temperature in water? Of course, it's absorption of plasma, linear absorption. And this plot proves this assertion. So here we plotted the refractive index measured after 1.5 nanosecond after excitation. So this value is proportional to the temperature. Here is product of laser fluence and refractive index measured after 2 picoseconds after excitation. So it's a number of carriers which we produced. And you can see that this is, before saturation, this dependence is a linear dependence, good linear dependence. And this proves the hypothesis that the main source of plasma, of water heating, is linear inverse Bremsstrahlung absorption of plasma by laser radiation. By the way, in you evaluate the temperature from this condition, you found that this temperature is about 100 degrees. What happens if we increase the energy? Unfortunately, in this situation, you can see the shots that produced for laser energies up to 100 microjoules. The interferometry technique does not work in these conditions because the plasma that you produce has a very complicated structure. So you can see emission. This is already scattering of pumped light from this plasma. So we cannot apply, we could not apply the interferometric measurements, but we measure this scattering light and found that this scattering is exponentially depends on pulse energy. From our point of view, this means that at this laser energy, about 20, 30 microjoule in our conditions, we start development of electron avalanche in the water. So once again, this plot combines all the data that we measured. So we have two energy regimes. In the low energy regime, we absorb the light via multi-photon absorption and produce the carriers via multi-photon absorption. Then we heat this plasma via linear absorption. So here, this linear absorption becomes so high that avalanche process starts. Here we can achieve the concentration of plasma 10 in 19 carriers. Here at least 10 in 92 carriers per cubic centimeter and maybe more. Here plasma lives about 200 picoseconds. Here in this regime, we don't know exactly how much, but we believe that this time is much longer due to high temperature of electrons. And let's talk about nanoparticles formation. Here you can see the experiment. So this is aqueous solution that we irradiate. This is laser pulse. This bright cloud is a scattering, which I told before. Red color, it's a photoluminescence emission. We measured this photoluminescence emission, the kinetics you can see here, and found that these kinetics is described very well with the classical equation which describes nanoparticles formation. So it's a very, very typical condition of gold nanoparticle formation in water. Here you can see absorbance spectra before and after irradiation. You can see appearance of plasmon peak. The spectra of dynamical scattering and TEM photos also demonstrate that we have deal with the gold nanoparticles of about several nanometers, which sometimes coalesce in the big clusters. So we characterized the rate of gold nanoparticles formation using plasmon peak magnitude. And corresponding dependence you can see here. So this dependence is threshold-like, and this threshold is about, in our condition, is about 50 microjoules. If you compare this picture with the picture describing properties of plasma, you can see that this value, about 50 microjoule, is threshold of avalanche development in our condition. And so our conjecture that the main feature to realize, to initiate photochemistry in the water solution is move into the avalanche regime. And probably the concentration of carriers is not the main feature here. We try to get nanoparticles formation in low energy regime, increasing the dose of irradiation, but we found nothing. Probably the main feature is a mobility of carriers. Solvated and wet electron is too immobile to travel through the medium and reduct metal ions. But when you heat this plasma, you can make initialization of photochemistry. And let me conclude. First, this work reports the dynamics of the optical properties of water ionized at very high laser intensity. Second, the multi-photon and avalanche regimes of an optical breakdown in the water were demonstrated our dominance for the lower and higher laser energy respectively. And third and minor, the onset of nanoparticles formation correlated with the avalanche development, suggesting that despite relatively high number of carriers, the solvated plasma is incapable of initiating the metal ion reduction. The possibility of the chemical reduction arises only when the photoexcited electrons appear in the quasi-free state. This work was supported by the Russian Science Foundation, and thank you for your attention very much.
Thank you for an interesting talk. It's a pity that there are not many of us here. Probably it would be interesting for me, for other researchers. So, questions, please, or comments?
When you investigate your bubbles in the water, have you tried to hear it or to register the sound of that process? No?
Not. We understand that this process is, of course, you can do it, and there are a lot of work that do these tasks. In our experiments, these bubbles interfere our measurements, because to measure plasma, its properties, we need accumulate information and measure again. And we could not do it with a high value, with a high repetition rate, because these bubbles interfere us. We have to wait when they disappear. So we make some delays between next pulses and so on. And from this point, we know that disappearance of bubble takes place in at least half second. So it's a slow process, very slow process as compared to this study.
Okay, other questions? I don't think that I have to ask questions because I'm co-author of this work. But I would like to comment that today it is already the third paper on laser interaction with liquids. Two of them were devoted to CVD, chemical deposition of metals from liquids, and this one concerns the interaction of intense light with liquid. So probably it's a kind of a new trend in research. Probably not, but at least I don't remember such a concentration before on our meetings. So, no other? Then thank you again. And take the
Okay, colleagues, and I would like to present the next talk. It's titled Anisotropic Structuring of Germanium
GST225.
Thin films by femtosecond laser pulses. It was done by Dr. Kolchin, Lomonosov, Moscow State University.
Thank you. Hello, dear colleagues. GST225 is well known as a basic material for development of nanophotonical devices, logic elements, and writable memory. Femtosecond laser irradiation of GST225 initiates laser-induced periodic surface structures formation, as well as ultra-fast phase changing. In turn, phase changing accompanied with ellipse formation provides data encoding in GST225 base memory devices due to artificial anisotropy. Thus, we set the next tasks in our investigations. Amorphous thin films on dielectric substrates were deposited in scanning mode by femtosecond laser pulses. After, we used the next experimental equipment for the diagnostics of initial and irradiated samples. Optical microscopy and scanning electron microscopy techniques show the formation of laser-induced periodic surface structures. These ripples demonstrate these ripples are directed orthogonally to the laser polarization with a period 150 nanometers to 1150 nanometers, and such a value is close to the laser in the incident laser wavelength. Such structural properties indicates that ripples can be formed by surface plasmon polariton excitation during photointensive photogeneration of free electron free charge carriers. Raman spectroscopy show that surface modification is accompanied with phase changing. Firstly, Raman spectroscopy data confirm the amorphous structure of initial GST225 samples. The amorphous structures was confirmed by the wide band from 110 back centimeters to 200 back centimeters due to intersection of 5 oscillations. In turn, Raman spectra of the irradiated area demonstrate the transition into the face-centered cubic crystalline phase as a result of reconfiguration of germanium telluride of germanium reconfiguration. As well, two-temperature model can describe phase ultra-fast phase changing, and we used for this description two-temperature model. And two-temperature model simulation shows that the lattice temperature at the surface of thin film and at the border between film and substrate exceeds the temperature of transition into face-centered cubic crystalline GST225 phase. And heat maps also indicates about possible crystallization through the depth of the GST225 amorphous film. Additionally, electron EDX spectroscopy show that the femtosecond laser irradiation doesn't allow to the stoichiometric parameters of GST225. After we started to investigate optical and electrical properties of irradiated samples, and we observed the optical anisotropy in the near infrared optical range, and Brueggemann effective media calculation model show that alternating of amorphous and crystalline stripes with the period 1050 nanometers to 1150 nanometers possesses optical anisotropy in the range from 800 nanometers to 2000 nanometers. Contrary, electrophysical measurement showed that the anisotropy of conductivity can be described by non-homogeneous crystallization of amorphous irradiated area of amorphous GST225 samples, and as you can see, the conductivity in the direction which is orthogonal, which is parallel to scan lines, is on 1 to 5 orders higher than the conductivity in the direction which is orthogonal to scan lines. And the activation energy confirmed this hypothesis. Okay, conclusions of our investigation. First, we observed the simultaneous crystallization and ellipse formation at the irradiated area. Secondly, optical anisotropy in the near-infrared range is explained by periodic relief. And third, non-homogeneous crystallization of scan lines possesses anisotropy of the conductivity. You can see our team in this slide. Also, this work was supported by Russian Foundation of Basic Research. Thank you for your attention.
Thank you very much. Interesting presentation. This talk is open for the question. Any question, please? I have one question.
Okay.
You demonstrated Raman spectroscopy.
Raman?
Raman, yeah.
Raman, okay.
Before, if I correctly coach, before and after irradiation, on the next, on the neighboring, yes, usually this plot on the same slide, and because you plot it on the different slide, it's difficult to understand what to do you exactly. So only crystallization, maybe you produce some new Fanon lines. Can you comment this in detail?
We used Gaussian approximation for the analysis of Raman spectra, and Gaussian approximation, and after we used the literature data for the description of observed Gaussian approximations.
Okay, one more question. Oh, please.
What was the depth of your ripples? So you told us about the period, and what was the depth?
Oh, can you repeat, please?
What was the depth of your ripples?
The depth of our ripples were near 10 to 20 nanometers.
Okay. So, if there are no questions, we thank speaker again.
Okay, thank you.
So, and continue our work. The next talk will be made by Dr. Kuzyakin from the Lebedev Physical Institute of the Russian Academy of Science. Modification of the same thin film by femtosecond laser pulses under different irradiation modes.
Good afternoon, everybody. My name is Sergei Kozyukhin. Sorry. And first of all, I would like to thank the organizer of conference for the invitation, opportunity to make a presentation. Also, I would like to thank my colleagues for useful collaboration and phase change memory, short introduction to this phenomenon. PCM works due to the ultra-fast reversible transition between crystalline and amorphous phases. Often amorphous and crystalline phases have very different electrical and optical properties stemming from the large difference in the structure for the amorphous and crystalline phases. This difference can be used to store information for application, first of all, but also for other applications in nanophotonics. Three operations are typical for PCM devices: recording or reset, erasing or set, and reading of information. Set and reset operation associated with phase transition. The most studied composition among PCM materials is germanium-2, antimony-2, tellurium-5, or GST-225. It is used as a functional material for active region in optical data storage and electrical memory devices. In addition to optical and electrical storage devices, various device prototypes for nanophotonic application have been presented over the past few years, and some examples you can see here. But in fact, all these devices use just one feature of GST material: reversible phase transformation under the influence of an external influence, in particle and laser beam. But the functionality of PCM materials is wider from my point of view, and in combination with laser technologies, it is possible to observe new effects that have prospects for application. So we used thin films of GST-225 composition for our study, which were prepared by magnetron sputtering at room temperature. And here you can see the condition of fabrication of thin films. We used different methods to identify the fake composition of prepared films. We performed scanning electron microscopy, transmission electron microscopy, atomic force microscopy, X-ray diffraction analysis, temperature dependence of DC conductivity, and all obtained results confirm that as deposited films have amorphous phase. We have carried out an element mapping of thin films using EDX spectroscopy. And also this result indicates that composition of film corresponds to GST-225. The uniform distribution of the elements across the thin film thickness was determined by Auger spectroscopy. Based on this result, we conclude that all deposited films are amorphous with uniform distribution of the elements across the thin film thickness, and the composition corresponds to germanium-2, antimony-2, tellurium-5. Most research using pulse laser for PCM materials is associated with the problem of crystallization of amorphous state. As can you see, the set operation associated with crystallization is the slowest, and accordingly, it determines the performance of the device as a whole. The use of pulse laser allows to increase the crystallization rate, and our latest result of the problem of crystallization can be seen in these articles. However, the use of ultra-short pulse laser makes it possible to study other effects, in particular the formation of periodic surface structures or lips. As is well known, the spontaneous formation of lips under the pulse laser radiation has been studied extensively since 1880s, And this effect is observed in semiconductors, in metal, in dielectrics, as the basic experimental and theoretical regularities are known. We use Iterbium KGV laser system, and parameters of this system you can see in this slide. We perform the experiment as follows. On the same films, we change the number of pulses and energy influence with the fixed step interval and discretely change the position of the film relative to the laser beam. The summarized optical microscope images of GST225 amorphous film are shown in this figure. As can be seen from these images, there are several types of marks. Gray images correspond to amorphous phase. We identify white marks as crystalline areas. Black marks correspond to ablation process. The selected area the selected group correspond to the area of periodic surface structures or rip formation. These figures show 4 different images of lips obtained by different methods. Firstly, it can be seen that the ripple period is about 1 micron, which corresponds to the laser wavelength. Secondly, the height difference between the valley and the ridge is several nanometers. According to AFM data. In fact, we observe the formation of periodic structures that do not have a relief. Thirdly, the experimental data from optical microscopy and conductive AFM data suggests that the valleys consist on the crystalline phase, while the ridges remain amorphous during the laser irradiation. A more detailed study of the formed rips was carried out using transmission electron microscopy possibilities. The results show that there are periodic crystalline regions in the amorphous matrix. And this is confirmed by electron diffraction data. The period of these structures is equal to the laser wavelength of 1030 nanometers. These crystalline regions are located a few nanometers below the surface of the amorphous film. And they form valleys. We assume that the relative height change of the crystalline phase in comparison with the amorphous one is connected with the density rise and compression of this region. The next stage of our research was to obtain elongated structures filled with ripples. We have established the fluence of 2.6 and 3.9 millijoule per square centimeters produce the spot field with bands oriented perpendicular to the polarization of the laser beam. In case of the smallest fluence, we cannot observe modification of surface for any beam size. At high fluences, the crystalline spots or ablated areas were obtained. For the case of fluence 2.6 millijoule per square centimeter, there is a prominent influence of beam diameter. We recorded the two-phase gradient on the GST225 surface according to these determinate parameters. Here you can see the scheme of a measure of the binary gradient of on the GST surface by a scanning femtosecond beam. We use beam diameter of 137 micron for obtaining the widest stripe of the periodic structures. The required scanning rates were determined using this relation. The fluences were varied within the range from 2.6 to 3.9 millijoule per square centimeter. The polarization direction of the light was orthogonal to the scanning diffraction, which defines the direction of the ribs along the stripe. We obtained 1 millimeter long stripes with a regular structure due to the ellipse formation. It was found that in the use range of scanning speeds, the structure of the stripes do not change. However, it's noticeably sensitive to the value of the fluence. The uniformly filled with the two-phase banded stripes with the constant in narrow fluence range from 3.1, 3.4 millijoule per square centimeter. At low fluence, about 2.6 millijoule per square centimeter, the stripes had an irregular width, while at high fluence, about 3.9 millijoule per square centimeter, white crystallization area was formed in the central part of the stripe. Atomic force microscopy was employed to obtain the value of the grating period and the width of crystalline and amorphous band forming it. The height difference between crystalline valleys and amorphous ridges was about 8 nanometers. The crystal phase in the valleys and the amorphous phase in the ridges are confirmed by our previous studies. In the case of MAG, we observe the femtosecond pulse produce ellipse orientation perpendicular to the polarization vector always. And in the case of the change in the polarization vector, the direction of the ribs also change. Accordingly, we performed a similar experiment in the case of extant structures. Changing the polarization vector by 90 degrees also leads to the corresponding change in the direction of periodic structures, as can be seen in these figures. In case of scanning along the polarization direction, we observe the formation of stripes filled perpendicular periodic structures. The parameters of such structures do not change. The period is about 1 micron, and it corresponds to laser wavelengths. Thus, the recorded stripe is characterized by a regular two-phase binary structure with a period of about 1 micron, and its quality is proved by efficient optical diffraction. In the diffraction experiment, we use a continuous wave laser incident at an angle 45 degrees on the film. The laser beam was focused in such a way that its diameter, about 40 microns, was close to the width of the stripe, so that it completely fell on the one strip. A beam incident on a reflection diffraction grating produced minus first, minus second, and minus third diffraction orders. The powers of the diffraction orders were measured using power meter for true polarization. We simulated also the diffraction efficiency taking into account the parameter of GST225 thin films by defining the specific reflective index and extension coefficient. Figures show the comparison of simulated experimental values of diffraction efficiency. One can see a good agreement, experiment and theory for both waves. In conclusion, I would like to summarize our results. The parameters of the producer two-phase binary diffraction gratings can be widely controlled by laser radiation. Direct laser writing can produce large area high quality gratings. The recording gratings consisted of the amorphous ridges and crystalline valleys that are oriented perpendicular to the beam polarization, and this makes possible the inscription of complex surface structures by changing the polarization during the writing. This study in progress. The period of the gratings is governed by the wavelength of the writing radiation, and the depth of the crystallization crystallized region can depend on the radiation parameters. Thank you for your attention.
Dear colleagues, any question? Please, Professor Konov.
Were you interested only in phase in grating formation or in phase transformation as well? Because in case of large area phase transformation, you should also try non-polarized beam, because in this case you will avoid ripples.
We record is using only polarized laser, and please repeat.
Were you interested, or are you interested also in transformation, phase transformation of your material? Just phase, not grating, but phase transformation in a spot.
Yes, we study.
If yes, then we should use non-polarized beam, because in this case you can damp formation of ripples, which make your surface non-smooth.
Yeah.
Okay, next question. Next question, please. One more. I have one question. You have demonstrated a big map of laser spots on the film. Can you show it again? You have demonstrated big map of laser spots on the film with the different doses and different fluents. Can you show it again? No, previously. Где-то там 10-й слайд. Yes, this one.
This black spot, it's ablation.
Yes, and this is substrate, yes?
Yeah.
Okay. White spot, it's a crystallization probably. White spot. Results of crystallization.
In the case of fluence and number pulses, we can produce white spot, and white correspond to crystalline phase.
Okay. I note that under low fluence you produce white spot and then black spot surrounded by white spot as Gaussian wind, yes? But under high fluence this surrounding ring disappears. Why?
Because Gauss distribution of pulse, and we have in this case in the center ablation, in periphery crystalline.
Yeah, but for highest fluence this ring, white ring, disappears. Why? Only black spot. It's strange, not?
Because the energy is very high and we...
Okay, I see. Thank you. Any question? Okay, thank you, speaker, again. And next presentation will be done by Professor Aiji. The presentation is titled Laser-Assisted Synthesis of Boron Nanoparticles, Prokhorov General Physics Institute.
Good afternoon, dear colleagues. My name is Kudar Ayezha. I'm a postgraduate student at the General Physics Institute of Russian Academy of Science. And the topic of my presentation is laser-assisted synthesis of boron nanoparticles. Recent studies show that the use of boron nanoparticle as an additive in composite fuel gives significant increase in temperature in the conversion flame, which affects the energy intensity of the fuel. Boron is superior to hydrocarbons in terms of volumetric heat of combustion and in specific mass of combustion. For efficient combustion, the size of the nanoparticles should be as small as possible. And another important field for application of boron nanoparticle is boron neutron capture therapy for cancer cells. It's the destruction of cancer cells due to the accumulation of boron-10 isotope in them and irradiation with the neutrons. As a result, nuclear reaction occurs with the release of energy and destruction of the cancer cell. Currently, boron-containing chemical compounds are used in boron neutron capture therapy procedures. And the main disadvantage of these compounds is low content of boron. And use the pure boron nanoparticle can increase efficiency of boron neutron capture therapy. Nowadays, boron industrial powder with submicron size are prepared by chemical vapor deposition. And for efficient combustion and for efficient in boron neutron capture therapy, we need nanoparticles smaller, and the aim of this work is to obtain boron nanoparticle less than 100 nanometer. In this work, we use technique of laser ablation and fragmentation in liquid, and we use fiber ytterbium laser with next characteristics. Boron nanoparticle were synthesized in two steps. First, a laser ablation in continuous flow cell boron target, sinter target, and then a laser fragmentation generated nanoparticle solution. And on the next slide, you see a video of laser fragmentation of boron nanoparticles in a continuous flow cell. Radiation is supplied from the below the QA. We can clearly see plasma nanoparticles. And let's move on the result of laser ablation. Laser ablation has a character of spallation. It's mechanical damage, and in the first step, the main mass of particles is located in large particles. And to reduce the size of particles, generated solution was subjected to laser fragmentation, and the mass of small particles increases with fragmentation time, and particles less than 30 nanometer is still relatively high, and in size dominate. Another interesting result is shown by X-ray diffractograms. The diffractogram of generated nanoparticles differs from the initial target. It means nanoparticles undergo allotropic modification. They are made of rhombohedral boron and of elementary units of centrosymmetric boron 7. On the next slide, you can see a general view of nanoparticles with average size 50 nanometer and individual boron nanoparticle. And these nanoparticles have boron carbon-containing shell, and it's graphitized carbon. And tracing of the elemental composition of the particle across its diameter indicates that carbon content is homogeneous in the central part of particle and increases on its edges. Therefore, this carbon shell covers the whole particle. The Raman spectra of obtained nanoparticles differs from initial target and differs from amorphous and crystalline industrial powder. And in some areas, characteristic peaks of disordered carbon material D and G are visible. In our recent work, we studied the combustion of industrial amorphous powder, and the addition of boron increases temperature in flame front by 150 Kelvin. And we think that the resulting boron nanoparticles smaller than 100 nanometer will burn more efficiently, since the burning rate is proportional to the specific surface area of the particles. And having experience in obtaining nanoparticles in continuous flow cell, we obtained iron-buried nanoparticles by laser ablation. Iron-buried target enriched in boron 10 isotope, and nanoparticles are magnetic and can be collected using a permanent magnet. The average size of nanoparticles is about 50 nanometer, and the content of boron 10 isotope in ablated iron-buried nanoparticles is around 76.9%, while in industrial boron powder is only 90.2%, and the resulting iron-buried nanoparticle and industrial powder were studied for biocompatibility and in boron neutron capture therapy for cancer cells. And MTT assays show boron microparticle is biocompatible and have no cytotoxicity. But iron-buried nanoparticle is toxic. And irradiation of boron particles by a neutron leads to drop of survival fraction cells for microparticles up to 1%, for iron-buried enriched boron 10 isotope to 35%. Now I would like to finish by emphasizing the main points. Nanoparticles of elemental boron are generated for the first time by laser ablation and fragmentation in liquid. Nanoparticles with average size of 30 nanometer have carbon-containing shell, boron submicron particles increase temperature in the flame front by 150 Kelvin. Boron submicron particles decrease survival fraction cancer cells to 1%, and for iron barium nanoparticles to 35%. Boron nanoparticles are also of high interest in boron neutron capture process and as an additive in composite fuel. I would like to thank my colleagues, Russian Foundation President's Grants, and Prokhorov General Collective Use of Prokhorov General Physics Institute. Thank you for your attention. I will be happy to answer your question.
Thank you. This talk is open for discussion. Any question? Please.
Okay. Thank you very much for your presentation. And my question is, do you need to stabilize boron nanoparticles after laser synthesis, or it's not necessary? And if you carry out your technique in isopropanol, is it possible to some reaction or so on? What do you think?
If nanoparticles have a small size, less than 100 nanometer, it's stable for 10 hours, for 11 hours, and
you mean stabilization of the size, and after that,
if nanoparticle have small size, less than 100 nanometer, it is stabilized for 10 hours.
Okay, thank you.
Thank you.
Okay, thank you. One more. Okay, I have a simple question. You said that nanoparticles that you produced are surrounded by carbon shell.
Yes.
The question is, does such a nanoparticle preserve its unique properties about which you said in the introduction, fuel, cancer, and so on?
We think carbon shell maybe help for biocompatibility, because carbon don't influence in bio cells.
So it's unknown yet.
Yes.
Okay, thank you. Any more? Okay, thank you very much again.
Thank you.
And last presentation for today, it's titled Nanostructure of Polymer Surfaces Mediated by Colloidal Microparticle Lens Array by pair of femtosecond laser pulses of different colors. Was made by Dr. Afanasyev, Institute of Applied Physics of Russian Academy of Science.
Okay. Thank you very much for introduction. Let me introduce my talk. I am from Nizhny Novgorod, Institute of Applied Physics of Russian Academy of Science. My talk have wide background by authors who already succeed their talks here yesterday. So, first of all, I make an overview of scientific problem. When I pay attention to materials and some particular preparation. After that, I tell you about experimental step and experimental study, and we will demonstrate result of irradiation for two different types of material. Our ideology is as follows. When high power femtosecond laser pulses are applied to dielectrics, a plasma is formed in substance due to multiphoton or tunnel ionization. If energy of appeared electrons in conduction zone is higher than bandgap energy, impact ionization is possible, leading to appearance of another electron and so on. organizing avalanche-like process. When you released within radiation region with irreversible changes in the structure of the electric, you can find the laser ablation structures. In the generation of initial electrons in conduction band occurs due to multiphoton ionization, the efficiency of which strongly depends on photon energy. So a certain number of photons are necessary to gain the energy in the band gap. When the idea for our surface modification is using two Coulomb pulses of two different energies of photons. One is the main frequency, which is usually in infrared range, and another one is the second or high harmonic. We use the second harmonic. So the theoretical study in our group was organized about practically 20 years ago, but experimental study will start after that, and we make such kind of experiments about 10 years. Our experiment close to Corcom ideas figured in this paper, and we make our own study in following paper. We've called it particle length array assisted nanoparticle band harmonic of femtosecond laser. The high energy second harmonic photons of second harmonic generates free electron much more efficiently than fundamental frequency, the energy of which in turn is well absorbed by free electrons. So we have such kind of ideology to separate the mechanism of interaction of matter with photons of first and second harmonics. After that, we came to idea use microspheres deposited on the surface, organizing close-packed single layer. And after that, in certain rocks, we improve the density of recording such kind of structures to about 500 million structures per square centimeter. Pictures are demonstrated here. This time we like to pay attention to experiments with time delay between photons of fundamental frequency and second harmonic to find what is more rational to use. What are the sequence of pulses more useful for laser nanopatterning of such kind of surfaces? I mean polymer surfaces. Let's go to materials. So we should organize the processes of different absorption of photons in case of resonant media, which was polymethyl methacrylate, where broadband of absorption have its red border in more wavelength when the photons of third harmonic. It means the process of two-photon absorption, photons of first harmonic and the fundamental frequency and second harmonic simultaneously. And non-resonant material with the commercial olefin copolymer named topaz. We use the most ultraviolet we use polymer with less absorption in ultraviolet region, so we use modification of topaz 8007. But we have the problem with residual solvent, what was solved with aniline at the temperature higher than glass temperature. That was useful not only for eliminating of toluene, but in purpose of formation very smooth surface. Here you can find atomic force microscope images which demonstrate our prepared surfaces for sphere deposition and following irradiation. We have very low noise on the surface. These polymer layers are deposited on quartz plates. After that, we organize microsphere deposition in close-packed single layer. Here you can find images of multi-domain structure of single layer on polymethyl methacrylate surface and on the topaz surface. It was a problem because of weathering wet materials, and so you should organize such kind of process what form exactly a single layer. Experimental setup consists of some functional parts. That's the laser part, the delay line, and the place of laser interaction with the sample. We use titanium sapphire laser, what generates 50 femtoseconds pulses with about 1 microjoule at the exit of a laser. But after that, to obtain a certain ratio of intensities of first harmonic and the second harmonic, of fundamental frequency and the second harmonic, we use filters to align our scheme and find the zero of the delay line. We use BBO crystal as well as for initial generation of second harmonic. Because of different threshold of surface non-structuring, we use two different geometries of laser beams because of for polymethyl methacrylate it is sufficient to organize coaxial scheme, but for topaz, where the spot of laser beam of second harmonic is much smaller, for further investigation with atomic force microscope, we organize the follows process. We find we organized such kind of spot of fundamental frequency which is much smaller than total beam. It's sometimes about 2 times wider than demonstrated here, and at the threshold border we applied the beam of the second harmonic. And after that, with obtaining free of microspheres fields, we scan with atomic force the area exactly at that point of about central part of spot of second harmonic and place where the fundamental frequency is insufficient for obtaining ablation craters. Results of nanoparticle of polymethyl methacrylate are demonstrated here. Applied peak intensity about 1/2 terawatt per square centimeters, and we can find what the delay time of between pulses of second harmonic and fundamental frequency makes structures less in depth. But when we apply synchronous action of fundamental frequency and second harmonic laser pulses, we get very narrow and very deep ablation craters. In our situation, we have nanopatterning of topaz. Applying peak intensity was about 2 terawatts or higher per square centimeters. Leading second harmonic pulse with delay time of about 133 femtoseconds make some such kind of structures with no rims around the structure, and we can find the narrow pits. And the leading fundamental frequency pulse with delay of with the same delay time organized wider structures with rims and not so deep under surface level. After that, we try to find the statistics for obtained structures, but we have found what they are too noisy. For that, we organized additional excavation, what published this year in this paper. We have found what parameters of the structure depend on surrounding of each microsphere, what acts as lens on the surface. On these pictures you can find what the effect of edge lens is compared with the studied effect on time delay or on delay time between pulses. In summary, we calculate the statistics for such kind of structure for polymethylamide chloride polymer and for topaz polymer, and find what for resonant material it is more efficient to use simultaneously propagating pulses of fundamental frequency and second harmonic. It can be explained by more efficient absorption of two photons, and in case of non-resonant material, we can find such kind of process only using two photon of second harmonic, but second harmonic is much weaker than fundamental frequency. Moreover, as I demonstrated above, we have difference in non-resonant material in size of the structure. So if we like to obtain the narrow structure, the with the smallest size, we have to use leading second harmonic because of first harmonic is when the first fundamental frequency is in the lead, we can get only very narrow structures. So the conclusions as follows: we show what a resonant medium most effective in radiation with delay time equal to 0. Contrary with non-resonant media, the most effective is radiation with blue pulse coming first. Our explanation is as follows. Two photon absorption in generation of seed electrons in conductive band is more active for fundamental frequency and second harmonic process dominates, while in topaz we can't organize such kind of process. The role of fundamental frequency in case of topaz is energy absorbing for seeding electrons what appeared due to acting of second harmonic photons. And for our methodology, the employment of array of microspheres allow obtaining a huge amount of realization of a laser interaction process just for a single pulse. So you have no need to organize scanning with high numeric aperture objective for obtaining much more experimental data. This provides possibility of statistical filtering of structures parameters, enabling clear distinguishing of observed dependencies against the background artifact associated with surface inhomogeneities, scratches, and so on. This work was financially supported by the Russian Science Foundation. Also, with thanks to Alexander Krugulov from Lobachevsky State University for helping us in atomic force microscopy. Thank you for your attention.
Thank you, speaker. And this talk is open for the question. Is there any? I don't see. I have one question, very interesting talk. Is it correct that the intensity of both delayed pulses was approximately equal? Intensity of pulses.
Intensity of pulses applying in two different cases?
In many cases. How much difference was between them?
About 1.5 or 2 times greater in case of non-resonant media.
Okay, to demonstrate effectively the coupling between these delayed pulses and demonstrate that your idea is correct, it's interesting to see, maybe I miss, it's interesting to see on the surface when you apply only one blue or infrared pulse. Do you show this, maybe I miss?
We make some such kind of investigation and we have our works about, I believe, 8 years ago, where we use only one fundamental frequency, and followed by the spot with different the range of energies, and we find various realization structures and so on. Even with more tough materials, such kind of optically bad quartz, because for good quartz our energies are not sufficient with very tight focusing of the beam. But in that case we obtained not ablation but swelling bumps on the surface.
Okay, thank you. One more question. Okay, thank you, speaker, again in this case. And I close this session for today. Thank you, colleagues. It's all.